Okay, shall we start? Yeah. So, good evening, everyone. Okay, welcome back to Plan258. Yeah. So, this is the agenda for today. So, you will continue the group presentation last week, okay, beginning, and then we'll discuss a few topics. Today, group decision making. That's supposed to be the asynchronous class last time. Uh, uh, Mainly about development. Yeah. And then I will discuss about voting cooperative games, and then the main part is in IFN power dynamics. Yeah. Okay, so uh, for the group presentation, who want to present first? The one that did not present last meeting. Okay,
Hello,
yes. So I
I
will,
can present, sir.
yes, you can present. Yeah. And co-host. Okay, go.
Uh, is this visible, sir?
Hmm.
Okay, okay,
How about the others? Can you see this? Okay, good.
okay. So, we are the specialists, and this is our presentation tree. Uh, as a recap, we have uh, our study area is residential subdivisions in Dasmariñas. We have refined our scope. We mapped the particulars now.
Mhm.
So there are four subdivisions, and we identified the gates, and we just introduced today, or I mean, in our recent updates, the players being the average residents of the four subdivisions, and the public or represented by the government. So this is the recap of our uh, scenarios. The first scenario is leveraging on the security. Uh, so so in this scenario, all the gates to the subdivisions are closed. That will correspondingly lead to some congestion in the area. Second scenario would be the present restrictions. It's a hybrid of open and closed gates, with some gates having to or requiring pass-throughs to pay toll or to have stickers. Third will be the all gates open scenario. Uh, this will in our intuition, this will reduce traffic in the surrounding area, or just spread the demands uh through this through these streets. Uh, so we're predicting crime using we got the crime data in the city, and we investigated several factors, but what we found as significant to its contribution is just the population. So we have 0.41 r squared. Uh, it might not be perfect, but it will be for the purposes of this study only. So in the first scenario, we derived uh, hypothetically that there are zero crimes if there are no uh, population that will go inside. This is oversimplified, but that will be the assumption for now. Uh, Second scenario. So we are using an isochrone to identify the how many population will be caught in the surrounding areas when the gates are open. So once the gates are opened in the second scenario or the present scenario, uh, we estimated in from node 2 or from Manuelaville, they will catch 361,000 persons within 3.5 kilometers, which is equivalent to 323 crimes. This might not be the real or the an accurate estimation, but once we treat all the scenarios equally with the same uh, crime estimate, they are all comparable to each other. So this is the fully open scenario uh, from node 1. So it's different depending on the node. It's slightly low on crime for some reason because it's from a different node. So this is just snapshots of these are just snapshots of different population catchments from different nodes from the four subdivisions. So I just we haven't done all catchment analysis yet because it's a lot of
Mm.
data computation. So these are just snapshots for now. But in the end, we will have derived crime uh, as a number to represent the scenarios. Then for the traffic, I'd like to introduce this theory that I've been doing research about. So for simplicity, it just uses network graph analysis, the betweenness centrality and closeness centrality, and applied it to urban streets. Then there are a lot of application using network graph analysis, and the unique part in space syntax, the theory I'm talking about, is they're treating entire lengths as nodes. And for example, in this uh, map, this straight segment is considered one node, and then when it intersects with another, it's another node. So just like in this illustration, when it's uh, intersecting, it's connected by an edge. So it's just an application of the network uh, graph theory. And what's good about it is we can predict the accessibility of space even before constructing, or so it's really a useful tool in layout planning. So one of the three of the useful theories or somehow considered laws in the space syntax literature is natural movement, where it just say when the space is easily accessed, there is more movement in that space. And that's natural movement. So more accessibility, more movement. And then for the second law or theory is the movement economy, where it just simply says when there is accessibility and movement, there is corresponding potential for economic interactions. And lastly, the foreground and background, there is it just emphasizes the dichotomy of the more accessible space turns into an urban activated area or commercial use. On the other hand, the less accessible area will be residential. So this is just a quick run through. So how do I remove? Okay. So we gathered from the DPWH annual average daily traffic and paired it with the corresponding uh, spacing tax measures. We'll just skip through for now. And there is an we did a regression again and we got R squared 0.74. I think it's im imperfect because of the high intercepts, but it will work for now. Uh, so this will be our basis to anticipate every scenario's corresponding traffic. So we're gonna make a lookup table for the combination of closed and open gates. And then that's what we'll use to not only form the payoff matrix, but also create the optimization model. So we'll use a lookup table iterating every possible scenario. Uh, I tried, sir, to maybe integrate the calculation of centrality in the linear programming, but it might be overly complicated, so we'll just make a lookup table.
Okay.
So uh, once we finish all those data, we will have a payoff matrix. So there will be uh, the four scenarios. I mean the three scenarios and one more scenario that I will explain later, and two actions for the government, which is the natural movement, which means we just allow it as it is, versus there is an intervention that we will call supply management or uh yes, that's it. So per cell there will be corresponding resulting crime for the average resident, and there will be corresponding resulting traffic that will be in the interest of the public. And then we will we're try later I will try to propose scenario 4 and the supply management side. At first we are planning to do it through linear programming. I think we still can, but uh we'll see. I will just propose first some later. So just a recap, these are the scenarios. So I explained this already.
Okay.
Then this is the proposed uh scenario. But the idea is we will focus on location support or investing on the location through permeability. I mean, we will make the residential subdivisions permeable, but take advantage of the traffic generated by investing on the space. I'll just explain some local precedents. So, usually in Dasmariñas, all subdivisions or all residential subdivisions have uh, strict zoning inside. So it usually is just residential, and this specific subdivision is just new. It's it somehow is a game changer in the local area that one of the private developers developed this avenue and interconnected in and through the existing subdivision. And the reaction of the locals is to use that opportunity to create commercial, uh, to use their lots as commercial investments. So this is just an example of it. Then I'd like to just introduce what managed means too. So it's also common in the area that there are barangay outposts so that they can surveil the area for any issues, and there are CCTV cameras. There are also, as mentioned from our previous presentation, curfews. So that's just an idea of what managed means. There's also a local precedent for activating streets in the area. So one is by the city government. They created a broad street with commercial strips at both sides. And there's this recreational lifestyle strip where recreational bikers or um, locals enjoy the broad streets to have recreational activities, exercises, and stuff. So that's just a background on the area that it is not that uh, alien to the area. So in the specific context of the site, there's this high traffic public market in the north, and there's this low traffic public market in the west. There's also this somehow dead mall in this southwest area of the site. So just thinking of our heads, it's just it's like an opportunity to create new connections and develop the streets to be permeable and or walkable as a lifestyle and commercially activated street. So just sketching over. So the practical step would be to open some specific gates,
Mhm.
the relax zoning, strengthen security measures through the mentioned precedents, address traffic demand because there will be a change in traffic, which we will try to uh, estimate, and activate the interconnected lifestyle streets through street development. And then therefore we will have reduced traffic congestion, especially in this intersection where I forgot to mention that this is a critical congestion point that actually inspired this study because all traffic goes through here, and there's a lot of alternative routes that could have been uh, publicly available but are hindered by the uh, enclaves. So, and while we make these subdivisions permeable, we will pair it with uh, uh, security measures. Now that's not how that's a narrative, but maybe we will have what do you call this? An intersection from the derived linear programming and this narrative. So we will just try to explore, but I think there's a lot of factors I introduced here. I don't think we can all
Yeah.
account that. in a payoff matrix. So
Okay.
in the end, we will have I think this is I think we I just this is just
Okay.
okay. In the end, we will still have an MCDM just to justify the scenarios or just to illustrate the different scenarios. But we just added the game theory payoff matrix to help in the project.
Yes. So mechanism design probably will help. Yes. I want to ask several things. Who developed this area in residential? I mean the road. Who developed and then who will maintain the road?
Which ones are in
The one that
NMs?
you put in the slide a while ago. So for example, this one. Yeah. So this red, no, I know
Sorry.
this one inside residential is the developer of residential is the one who developed the road, right?
The existing, sir,
Yeah.
yes.
And then who will maintain this one?
Uh, so the proposed development assumes that the public or the government will take
Yes.
over because it
Correct.
will activate it like the congressional avenue that
Right.
I mentioned.
Okay. So usually I'm not sure what is the case in the Philippines. So in Indonesia we have a law that certain number of residential must be low class and then certain number must be medium class and can be high class in the same compound. So this is to reduce the social gap. Okay, that is by the law. So
Yes, sir.
probably you can introduce this also because the one that you introduced there, it seems like the gap between the rich and the poor is too high. That's why there is sense of insecurity happening because of that. And because you create very big gap, then the sense of insecurity is happening. And in fact, in Indonesia, you see even very rich residential area, uh, all gates are open. There is no gated community like what you have in the Metro Manila. Okay, so but after certain time, okay, then the developer will give this maintenance of the road, okay, to the government. That means before government approve the residential area to be developed, they need to check the whole scenario of their own budget. So this is a feedback mechanism. You understand? Uh,
Yes.
the government cannot just approve without thinking of their own budget to maintain the road. Right. Without this kind of check and balance system, then what happen is government just approve, and then not taking any responsibility. This is moral hazard, like in what we discussed last week, right? So approving residential area, that means also taking responsibility to maintain later in certain years. Okay, so and I have asked, are you not forcing to use certain tools for not sure if this is the right tool for the problem, for example, the linear programming. So, what is the connection between the space syntax to the topic of gated community?
Uh, so I actually skipped actually skipped to 3 slides. Oh, so this
Okay.
is an example of how space syntax illustrates the difference in the scenarios where the gates are open or closed.
Okay.
So in scenario one where all gates are closed,
Mm,
the so for context, the red ones mean uh high accessibility,
mm,
and the cool colors or the blue are low accessibility. So once the gates are open, there are alternative preferred routes through this subdivision that turns red. which means it's really a relevant part of the network. And for example, this one, it's this segment turned red, so it's a
Hmm.
preferable path.
Okay.
So once it's all closed, all paths just are strained in this other areas or other paths. So it's just a good illustration, and it's just how it has a number, so it can be quantified and compared
Okay.
with.
Okay. So is it possible to open only certain main road and then still keep the remaining residential area?
Sorry, sir.
Is
The
it possible to open only certain main road? For example, in this from uh, this line, I don't think I can. Okay. For example, only this road will be open.
Mhm.
Okay, and then the rest still close.
uh
Only
it,
certain street, for example. This can you see?
yes, sir. Yes, sir. I was thinking about that, but there are practical obstacles like existing houses, or how do you close off a street, uh, like there are a lot of streets, for example. How do I okay, maybe how do I
Yeah, I'm not sure. This is just conceptual, so you
yes,
probably
sir.
want to
So
connect certain thing. For example, here,
for example, sir, how maybe just a practical
uh,
uh how do we close off every street so that they are, let's say, they are isolated and they are safe, so there will be a lot of gates in there.
mm,
so so and who will manage those gates? So that's is
that's
there a
another
security for
problem.
it? So maybe that's just my thought,
Okay, so
but yes, we can simulate
mm,
those scenarios.
or probably this part is open, become a new road. Is it already much major road? So then can go directly to this line,
Yes, sir.
right? So rather than opening the residential area, I'm not sure. Anyway, there is IFN powered dynamic calculator. I will introduce you to later, and it has almost all the centrality that you talk about. So
Mm.
equivalence centrality, closeness centrality, all is there. You just input the matrix, and then you will get all.
So,
Okay.
sir, I'd like to ask, how do you represent space? Do you what are the nodes? So is it the intersection? Oh,
Then you define your own node. So in this case,
okay.
uh, node usually intersection or in power dynamic, the node represent agent or factor. But because this is practically graph theory, so you can use for anything.
Mm,
Okay, not necessarily
okay.
used for power dynamic. Okay.
Because I in space syntax
I
we
know
used
you reverse it,
yeah.
right? So
Yeah.
understand. Yeah. So in fact, I have communicated a few times with Mike Batty from UCL, the father
Mm,
of space syntax. Yeah,
yes,
I
sir.
think back
Oh,
in 1990s. Yeah.
wow.
Yes. Uh, understood. Okay.
Okay, sir.
Uh, okay, good. Thank you.
Okay, thank you, sir.
So who else will present? I think one more, right? Is that correct?
Our group will present, sir.
Yeah, cool, cool. Uh,
Can you
hmm,
see the screen now, sir?
yep.
Okay. So for the last group, our project is about, just a short recap, the strategic hub locations for centralized EVT and VS hub operations in Metro Manila. And we regret to inform the class that we are only three members now, unfortunately.
It's fine.
Yes. So for our updates, these are just the changes for our project. So first, we changed the prospective locations of the hubs of EVT and VS. The reason for this is that we based it on the four quadrants of Metro Manila, north, south, east, and west quadrants. And then we selected three locations for each so that there would be equal representation for each quadrants of Metro Manila. So these are the new locations that would be tested on our simulations and our scenarios. So for our analytical framework, so we will still we also uh, streamlined the attributes that will be considered for this. So we have passenger demand, energy infrastructure availability, and average trip length for the positive attributes or positive drivers that makes a particular location good EVT and VS hub. While the negative attributes are cost of development, because obviously if it requires more capital investment, then it is not it affects the viability of the location. Distance from origin and destinations and average traffic flows. And our perspective here is the point of view of the TNVS operator. So we wanted to optimize the hub placement in such a way that it requires the minimal amount of investment, but will be able to service the larger area for our TNVS operations. And then our scenarios is actually we only have two scenarios that will be presented later, the mall preference and LGU preference. So it means that if the location is in a private compound like a mall, a private developer, versus the second scenario if it will be developed on a if it will be developed by the government or the local government unit. So it will be tested using three methods, the AHP methods, Brown Gibson, and ideal flow network by using these models. And these models are actually based on the attributes shown earlier. So to further expound the factor analysis on how these three methods are used to calculate the feasibility of each location, this will be presented by Sir Daniel.
All right. Continuing the conversation. So, the two scenarios explores if the operator is scenario one is called, we call it mall scenario. So that means the EVT and VS partners with a mall, particularly for example in their parking lot or in their parking building, while the LGU preference means we are partnering with an LGU uh LGU particularly, and therefore we are also answering their preferences. We actually also have a baseline preference, but we haven't run that yet. So just to show you, this is actually our uh the relationship of all factors and stakeholders. So, uh, as we imagine, the study is largely like a site suitability study, but trying to consider different data as well as differing preferences between the partner institution in each scenario. So in this graph that we draw, so we identify the factors into firstly into two extrinsic characteristics and intrinsic characteristics. The extrinsic ones refers to the characteristics or the data within the vicinity or around or outside the lot being considered, while intrinsic one is the characteristics of the lot. And however, more relevantly, the positive factors are the one on the left on the colored green. So that includes passenger demand, average traffic, average trip length, and energy infrastructure slash capacity. On the other hand, for the red or negative factors, you have traffic flow and distance from OD destinations, and of course, cost of development. The other data that is not on that does not have a black border are since this is preferably a uh highly quantified case initially. So these are some of the actual data that's available out there, such as the population captured, the range of PVT and VS, the service area catchments, daytime population. The cost of lot is also a variable of the proponent, zonal value, the size of lot, as well as even the partner institution. So however, for this study, we merely simulated the data based on so we set a baseline information or baseline data across all 12 locations uh and for each of those six characteristics, and we shall run them through different methods on IFN, on Brown Gibson, and on AHP. So, uh, wait lang. Could you go next slide, please?
Next slide,
Back
please.
slide, back. Yeah, yeah. So it basically it just wants to see if feasible and profitable phase two, say years 5 to 10 of ETNV's operation with stronger networks and partnerships. So with that said, perhaps we would update you on each of our products. So the way that we work is we try to test this suitability analysis through those three methods, and with one method for each of us three members. So could you go next slide, please? Uh, so could you share screen the Google Sheet, Paul? So uh perhaps we can begin with mine. So Brown Gibson. All right. I tried to run this. So the assumption here is the objective factors will be those of the cost, while it would be considered to be the subjective factors would be the positive characteristics. However, of course, influenced by the uh, presumed decisions of, say, an LGU partner or a mall partner. So yeah. So with that said, that is how I run our simulation. So just looking at the trail or the yellows, just scroll down. Yan. Just to show you the process. But perhaps could you scroll down further? So we tried it by scenario. So those are matrices. So with that, we presume also. Could you go up again? Sorry. Go to scenario one. Scenario one. Yeah. So for the scenario one, if you look at the pale yellow, we presume that they would prefer having the passenger demand as more preferred uh more preferred factor over energy infrastructure and average trip lengths. So that would be the basis of their subjective factors. So with that said, so kindly, and for scenario two, please could you show scenario two? Uh, yeah, for scenario two, could you go up a bit further up? Yeah. So, sorry, the passenger demand is for the mall, but for the LGU, it's uh, no. Could you look for scenario LGU? Hmm. Oh yeah, yeah, yeah. Down. Oh, oh, further up, please. Yeah. So the scenario for LGU prefers uh the average strip length. So that is an example matrix of the subjective factors. Now, with that, so combining the subjective factor and the objective factor, could you scroll down to the end of the sheet? The, so we computed with the assumed weights of for the LGU, we assume that they would likely have a heavier weight on the subjective score with zero point 0.6 and 0.44 objective. So with that said, the land called National Steel Corp is the one identified that would be most preferred. While for the second scenario, uh, partnering with a mall would prefer Lambingan. So Lambingan, yes, with the objective score, which we would presume they would be much more governed by numbers. So the zero point 0.7 weight for objective and subjective score for zero point 0.3. We tried to run a sensitivity analysis. So on the right, so we see that National Steel Corp is the one who won for the LGU appears twice in zero point 0.1 intervals. The other prominent one in this simulation is Las Piñas 0.1 and NSCR lot and Lambingan. For the model scenario, Lambingan appeared in five. Yes, five out of 11 of the zero point 0.1 intervals. Two for SM City Grand Central and 11 for Bridgestone. Interestingly, Lambingan is not exactly a mall. So we would have to see how that unfolds in our simulations later on. So yeah, could you go back to Canva? Or perhaps just a little thing to show. Could the last slide, please? Could you go to the Gemini?
Can you see the screen now?
No, no. It's still in the Canva.
What page again? Sorry.
The Gemini. Go to the next slide.
Okay.
That link. Yeah. And scroll down to the list. To the furthest down. So yeah, I was also trying to consult with Gemini this. But interestingly, uh well, just to share with the class, we can actually also do interactive graphs with the current generative AI. So maybe that's an interesting tool. Go to the furthest down. That's an interesting tool to explore. So that's what I. Yeah. Can you press that show me the vision? So you could try to interact with that. So,
Yeah.
yeah. So for example, something like that. So it's very similar to SURP's calculator in the website. So it was just an accidental discovery. Yeah.
Right.
Just to share it with the class. Yeah. Anyway, that's Paul, you could continue with yours.
Oh, so for our end, the other simulations mentioned earlier, we will use IFN and AHP. But for this case, the only the uh, mall scenario and LGU uh, are processed, and it is not yet identified until the sensitivity analysis part.
Okay.
And by using the steps of IFN, so the result is uh, the National Steel Corporation, which is the 10th location for the hub also came first, which agrees with the results of Brown-Gibson that has been shown earlier. And for the scenario of the LGU, it will still undergo sensitivity analysis later on upon the revisions. And for AHP, I think Rio is here.
Yes, hello. Hello. Just to note, the file currently shown on the screen is still the earlier working version. So it still have the old multiple factor setup and the old location we identified before. So right now, we are working to update it so it will be in line with the IFN and Brown Gibson.
Okay.
But in terms of process, we still follow the AHP process. First, we define the goal, then identify the alternative location and factor for evaluation. And then after that, we need the comparison of the factors to get their weights. And then we check the consistency just to make sure it is correct or it is acceptable. Then next, we entered the score for each location to the normalization, and then multiplied them to the corresponding weights. And then the scores were added to get their AHP scores, and then used to rank the each location. So that's the process or the flow that we've done for the AHP. Though as mentioned, we are still in the process of updating it to the six factor, similar to the IFN and Brown Gibson. So unlike the Brown Gibson and IFN, they already mentioned the uh, an somewhat partial result on the where location is the most suitable. But for this one, since it's not yet updated, I can't show you the most suitable location for AHP.
Okay.
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 That would be
Yeah, thank you. So I'm not sure if you're forcing certain tools again for the right problem or not. Yeah. So what is the actual goal? How many hubs will be developed out of the 12?
the actual goal is not about the quantity, but more on a recommendation on which hub is the most suitable. So it would be
Only
ranked.
one.
Yes, not necessary, sir. It will be ranked based on the scores of the three simulations.
Okay.
It
So
what we are eyeing is, sorry, I will share again if you would allow me, sir.
mm,
Okay, what we are eyeing is to at least, as I have mentioned, we have four
4,
quadrants.
right?
So at least one hub for each quadrant,
Okay.
so
So
that
in
there
that,
would be equal representation for each.
right. So in that case, probably yeah, prioritization is fine, yeah. But the factor are coarse and very nice subjective and consensus decision technique, yeah. But there are more refined method that you probably would like to consider. For example, one is the linear programming, yeah. So you want to find so that there are certain constraints, isn't it? That only 4, and then you will find one on each block, isn't that what
Yes.
you want to do, right? And then we did not discuss this in the class, but you can search. Yeah, there is what is called Voronoi diagram. Uh, Voronoi diagrams.
Um,
Yeah, I'm familiar with it, sir.
I'm sorry, sir.
So
How would you spell that, sir? I'm sorry.
yeah, I will type in that.
What kind of Voronoi?
Voronoi.
Ah, Voronoi.
Yes, Voronoi diagram.
For this one.
Yes. So, and then you can do a combinatoric analysis with Voronoi diagram so that you will get exactly what you want, and then where it will cover certain areas that you can use. But we did not discuss this in the class. I understand that. But yeah.
Okay.
Okay. So, of course, you still need to do a lot of combinatoric analysis for this purpose. Yeah. That will be more refined than just prioritization. Prioritization, you will give rank 1, 2, 3, right? But since you have constrained that actually 4 location, then that rank probably different from what you want, isn't it? So yeah, probably certain more refined analysis will be needed for that. One of them is what we discussed last time. So linear programming, because you can set the constraint.
Yes. Okay.
Okay. So that will be more useful for this type of study with more quantitative optimization. Okay.
So we will surely add the linear programming, sir, for our
Yeah.
methods
Okay.
for both scenarios.
Yes. Okay. Thank you. So if you have any other discussion from each group, go ahead. Yeah. Okay. In that case, let's start the lecture. Uh, okay, so we will discuss today. You can download the lecture note on this one first. Maybe group decision. Yeah, group decision analysis. I will. This supposed to be the discussion last time for asynchronous class. Right. Okay. So did you see my slide? Right. Okay. So I will not discuss the whole things you're supposed to read on your own. I'll just discuss a few things. Now, one is the Delphi method, and the other one is the last part, the N-person cooperative games. Yeah, the rest you can just read. Okay. Are you familiar with Delphi method already? No. Okay. So our goal is to create group decision. For example, in the team, in urban planning, you always have a lot of different stakeholders. Okay, for example, the government and you and the citizen and so on. So, how to create aggregation of individual preference? Okay, so this is the idea of a group decision. Okay, so of course we want to get what is called consensus, yeah, if possible. Yeah. So consensus means agreement made by the group that ultimately lead to collective decision. Uh, but be careful, the meaning of consensus, okay, often defined as 100% agreement. But this is not really true. Yeah. Consensus is not always unanimity. Yeah. So unanimity means 100% agreement for all the stakeholders. Okay. So when we say consensus, that means everyone just agree on something. For example, you want to go to movie with certain friends, right? So you need to reach certain consensus. Which movie you want to watch together? Otherwise, you will not watch together. Okay. So just make a simple agreement. So in that case, certain people will give up their preference in order to get a higher preference of the group. Okay. So when we said consensus, okay, strong consensus occur when the opinion is shared widely throughout the entire population, but not necessarily unanimous. Unanimous mean 100%. So in this case, even if you can get majority, so 50% plus one, it is already majority, right? So that case, it's already consensus. Is that okay? But a lot of studies about this group decision making. The problem is sometimes the group preference, okay, will make inconsistent problem among individual. Yeah, for example, this is observed a long time ago, several centuries ago, by Marquis de Condorcet. So this is the rank of each individual, say A, B, C, yeah, Ali, Budi, Buddy, and Sherry. So there are three alternative X, Y, and Z. And this create a kind of inconsistent problem. Okay, so in that case, what to do? Yeah, one is to just make a simple application. So if you have certain things that you want to vote, okay, then you create certain judgment, certain value. Okay, you put score 1 to 9, for example. Okay, and then each judge will have equal weight. This is the simplest, right? The problem is like a duck, okay? People tend to follow the others, okay? So people tend to follow the flock. The first one who estimate or overestimate, okay? Then the others will just follow that uh, crowd behavior problem, okay? In that case, reliability become problematic, okay? Because someone else who speak first will influence the others. So, for example, you can just simple aggregation. Say you have judge A, say 3 million, B is 1 million, C is 1 million, then you just divide, right? So another technique is to put certain weight for certain judge. Yeah. So that means you start to make each judge have different weight. Okay, so certain expert will charge higher weight than the other. So in that case, you can have, for example, if you say that judge A is 2 times more expert than judge B, and then judge 3 is 3 times more expert than judge A, then you can set the equation like this, and then you can set any number for B, okay, and that means if B is 1, then A is 2, right? And then that means C becomes 6, correct? So in that case, the sum become 9. So and then you can normalize the weight to create the weight for each judge. Yeah. So again, that depends on how you perceive each judge. Yeah. So with the same number of judgment, but if you put different weight, the result will be totally different. Yeah. The scoring will be different. Okay, now this is the main part that I want to discuss. So Delphi method is an iterative group decision process. Okay, this is very well known when the panel of expert will give estimate or weight or certain values. Okay, and each person has opportunity to re-evaluate, okay, his or her own response, okay, after a feedback about the aggregation value. The aggregation means either the mean or the median or the standard deviation. Okay, so the most important part here is independent, so that there is no flock following behavior. So the judge does not know the estimation of other judges. Okay, and the result usually converges after several rounds of feedback. Okay, so I want you to play this today. a Delphi method. Okay. So each one of you, okay, I will open Excel here. Okay. So each one of you will, can you see the Excel? Yes. Okay. Each one of you will give me an estimate of this mark. Okay. How much is the price of this mark? Is that okay? Simple, right? Okay. Each one of you direct message to me, not to everyone. Okay. And then I will just type there. Is that okay? Okay. So go. Chat with me. Oops. What currency? Okay, in pesos, no problem. Okay. Okay, 250, 300. Yeah, this is first round, okay? First round. Be consistent with your own value. Okay, so 300, 250, 300, 350, 150. Is that all? Okay, so then let's see. Let's take the mean and the standard deviation. Okay, so I will put here average and standard deviation as detail. Okay, let's say this is sample. Okay, can you see? We have on average. So in real Delphi method, I will not show you this one. Okay, because it should be independent. Okay, otherwise you will following the others, right? So I will just show you the mean. Is that clear? Okay, let's do the second round. Okay, second round. Okay, I will tell you, hey, that the mark average is 270 pesos. Okay, so I will not show you this one. So, but I will just tell you 270. Is that okay? Let's do the second round. The one who said 250 there, how much is now? Okay, still insists the same. So, okay. How about the one who said 300 earlier? Still the same? Okay, so 300, 350, 200. And 1, 2, 3, 4, 150. Uh, the one who said 150 earlier, how much? Mhm. Hmm? How much is the one who said 150 earlier? So how much is now your estimate? 200. Okay. Okay, so I'll just copy this. Okay, so now become 260. But can you see that the standard deviation is reduced? Okay, so this is the usual method in Delphi. Yeah. So after 3 rounds, usually the standard deviation will reduce so much. Okay, so of course you can continue as many rounds as you want. Okay, the technique is very simple. Yeah. So you will not show this one. Okay, so the actual value will not be shown to others. Okay, but only the mean and standard deviation will be shown. Is this clear, Delphi method? Any question? So you can do this, right? So very, very simple method, okay, that you can always use it also. Well, yeah. So say you can use this for cost of development project or your hub or whatever that based on your projects. Yeah. And then what you will do is just given your own opinion, either based on data or your own opinion, and then compute the average and standard deviation. Okay. And then ask them to reconsider back. Based on that average, what will be the next opinion? Yeah, usually people will change based on that feedback. Very simple technique. Delphi is the name of city where this technique started. Yeah. Okay. So the rest, this one I will just skip. Yeah. So Condorcet earlier. Why this is paradox? Okay. So this is the judgment of a say you have three judges, X, Y, Z, and these are the name of the project. Yeah. Okay, C, A, B, C. Okay, and each will judge differently. So what happened is because each will have this preference. Okay, what you will see is look at the comparison between each two. Okay, so the number of vote A is larger than B. How many? This one is A larger than B. This one also larger than B. So A get 2 vote. Yeah, B get only 1 vote. And then if you look at B larger than C, the same, yeah. And if you look at so if you just look at these two, yeah, A larger than B and B larger than C, you will conclude that A is larger than B and larger than C, right? So, but if you look at C larger than A, again, you will get exactly the same form. That means this is a contradiction. Okay, the one who vote first will win. In fact, there is somebody can cheat, okay, by not revealing their own preference. If they know the other preference already exposed, then they can cheat so that they can win with their own preference. Yeah, this is what happened. So a Nobel Prize winner named Kenneth Arrow, yeah, telling 4 conditions, okay, of Arrow. This is called Arrow impossibility theorem, and he got Nobel Prize winner Nobel Prize because of this theorem. Okay, he proved mathematically, okay, that actually it is not possible to have all these 4 conditions all at once. Okay, so can be 2 of them, can be 3 of them satisfied, but not possible to have 4 of them at once. So yeah, so that means the condition is talking about transitive, Pareto principle, non-dictatorship, and then independent. So you can have 3, but not 4. Okay, that is the one that telling. Yeah. So he won economic Nobel Prize for this. Yeah. So what is the point? This are impossibility theorem telling that the truly democratic system is actually almost impossible. Okay. Okay, so the rest is just voting type. So I will just skip. You can just read by yourself. But the last one I want to discuss is this one. Okay, in many voting situation, okay, you want to represent as a weighted majority games. Okay, so and this is very useful in many settings, either in politics, in the decision in family, or even in United Nations, or yeah, or in the business. Yeah, for example, the board, right? in a business usually have certain number of votes. That depends on how much they put their money in, isn't it? Okay, so then also in the politics, so there are what is called coalition. A certain party will combine their vote with other party to create a coalition, right? So you practically create a cooperative games, yeah. So you make coalition, mean you make a group in order to win together. Is that clear? So this is game theory actually, but not competitive. This is cooperative. Okay. So the technique is rather simple. Okay. So each person, I, okay, will have their own value, W, weight. And then we have also what is called quota. Yeah. So quota means the threshold. Okay. So the game have n players. So 1 to n. So okay. And then Q is the quota. That means the threshold. Usually, okay, unless you specify, yeah, usually we don't say the quota. If you don't say the quota must be like this. Yeah, you sum all of the weight and then you divide by 2. The quota must be larger than that. Majority. Remember the consensus a while ago. Is that clear or not? Okay, so this is what you will do. So in business setting, of course, you can create that weight depends on the company stock, right? The majority who own the stock usually have full control on the business. Yeah. So okay. So let's analyze this. Okay. Let's analyze this. So if you have all 1, okay, and then a certain Q mean half of that. Yeah. You sum all of that and then more than half. Okay. Then this means all players have equal power. Okay. So now, can you see this? Say the quota is 51. Okay. And then this is the weight of each player. So we have how many players here? 1, 2, 3, 4, right? So player 1 have 28 vote. Okay. Player 2 have 24 and 2, 3, 4 have 24 vote. So this means player 1 is stronger player than the last 3. Why? Because look at this, 28 plus 24, how much? 52, larger than 51. Right. That means this first player, yeah, can join with any one of these player 2, player 3, or player 4, make a coalition, right? And then they will win. Now you are starting to learn politics, no? How to you make a coalition with other people, isn't it? So, okay, by knowing this vote, you know what to do. Okay, so what happened to player 2, 3, and 4? If you combine 24 plus 24, how much? It's less than 52, right? So, meaning if they want to win, they need to combine the 3 of them against the stronger player, 28. Okay? The less number of player, okay, that means easier to make cooperation compared to many, isn't it? Is this clear or not? Any question about this? Okay, good. So how about this one? So again, the quota is 51. Okay. So if you have 26, 26, 26, and then 22 at the end, okay, 26 plus 26 is already 52. That means any of these 3 players, they just make coalition of the 2, okay, they will get the quota already. But this player 4 with vote of 22, it's powerless. Yeah. Right. Because any winning coalition containing this player, yeah, will just well win without this player, yeah, player 4. So now you start to see the power based on the fold. Interesting. Okay. So in UN, you heard that 5 member country, permanent member country, have what is called veto power. Okay. What is veto power? Okay. So this is the definition. A player or a coalition, okay, is said to have a veto power if no coalition able to win a ballot without his or her consent. Okay, let's take example. Okay, look at this. This is 50 less than 51, right? So player 1 in here have veto power. Why? Because player 1 can just combine with others to win. But the other player cannot combine into coalition in order to reach 51, isn't it? Look at this. The other player is 49 plus 1 is 50. 50 is below 51, isn't it? That means cannot reach the quota, the threshold. So that means in order to pass the resolution, this player 1 must be there always. That's the meaning of veto. Yeah. Now you can quantify the meaning of veto, not just talking. So you can quantify this. Interesting? Yeah. Okay, the same thing here. So this is, I can put the quota is 3. Okay, that means the third player, yeah, has veto power. Why? Because uh, these two, first and second player, if you want to combine into coalition, still cannot reach the quota 3. So must include player 3 in order to pass the resolution. Clear? Yeah, to make decision, player 3 must be there because of this rule. So by creating the system, yeah, voting and the quota, then you can play with this. And then you will know how much is your strength and power. Clear or not? This is the actual UN Security Council, right? So the 5 in Security Council you have 15 members. In UN Security Council you have 15 members, and the 5 is permanent, right? The next 10 are rotated every year by some vote, yeah. So even if they, and this is the quota 39. Okay, so can you make, for example, the 4 of them join together, that 28, and then plus 10 of them, that's still 38. Correct. Still cannot reach 39, so cannot keep resolution, cannot make decision. So this permanent member is important. Okay, unless the 5 of them agree, okay, so they cannot make agreement. Okay, but of course the 5 of them agree does not mean they can make agreement. At least they need at least 4 of the non-permanent member to make that agreement, isn't it? Clear the meaning of veto? Interesting? Yeah, you can quantify, yeah, politics, yeah, not necessarily just politics. So what is the meaning of tic-tac-toe? This is, okay, with definition, okay, with computation, so that you can see this, okay? So a voter, say, so this is 1, 2, 3, okay, is a dictator. Yes, yes, George, you want to ask question before I continue?
Sir, who determines or create the quota? Just like, for example, that's 39. So why 39? Why not 35 so that this 777 this
Good
power
question.
can
That's agreement in the beginning. When you create UN, you create that number.
so that is what they agreed, sir, 39.
Yes. So that the 5 will be no, that this number can be not necessarily 39. You can change because this is ordinal number. Okay. But this is the simplest I can put there. Right. So this quota and this agreement is where you put the basis of the company, the basis of the organization usually have this statement. Right? When you establish a company, when you establish an organization, you must state this agreement in the beginning, in the preamble usually. Also in the country, right? So you have certain voting systems, so usually in the constitution we have this. This is the game that you set in the beginning. Do I answer the question? Okay. So what we do is analyze that game, okay? Then we can start to see. Okay. Now, if you want to create a dictatorship, okay, let's play that. Okay. You don't need to be majority. Yeah. All you need to do is play the quota the same as yourself. You see that? Okay. So a dictator, if he control any vote by himself, okay, so that the weight is equal, not just yeah, equal or larger than the quota. So the quota is 3. Okay? Player 2 is dictator. Why? Because by himself, okay, he can already make decision. The other player here are dummies. Okay. So don't say dictator is the only one on the party. Not necessarily. You can make a lot of parties. Okay. But as long as the quota is the same as the power of the voting power, okay, then you become dictator anyway. This is something new, right? You thought dictator is one party system, not necessarily. Okay, can be multi-party, okay, as long as the vote is clear or equal, then the quota. Clear, yeah? So, okay, this is if you compute, okay, I create the calculator there, so you can just join the calculator and anyway, it's free, right? So, and then you will have the calculator that you can input this number, okay, the quota and the vote, and then you will see whether they are actually the same or not. Okay, so if the game give exactly the same power, then they are similar power. Yeah. Okay. Then you ask, how do I compute? The computation is a little bit more complicated than what I explained here. Yeah. So there are certain algorithm, bunch of index, and so on, that you need to compute all the combination. Let me check. Okay, this is Shapley index. Can you see the? So if you join the level okay, there is a strategic analytic you can join, and you can just set the quota here. Say for example 51, and then you can also set the player. Yeah, you can add any other player. For example, I put 10 and so on. And then you can compute the power index, yeah, using what is called Shapley power or Pansa power. This represents the combination. Okay. And there are many examples here that you can also check. This is the UN a while ago, right? And this is how it computed, yeah. So these are the UN Security Council. So This one is example of 4 players and so on. So you set the quota here, and then you can set the weight of each player. If you want to reduce, just delete 3 player. Okay. And then you will see, oh, this person have veto power, and this is have weak power, a player, and so on. So it will give you the interpretation based on combinatoric. Yeah. If you want to know how it computed details, so you click this one, you will see the graph and the matrix. Yeah. So basically, we computed all combination, and then compute the weight. Yeah, whether if this combined with this one, what will happen? If that one player combined with other player, what will happen? Like that. Based on this, you can compute the power. Okay. Okay. Then so the group decision start. So again, sometimes you want to see whether these 2 voting influence are identical or not. Yeah. So if they have the same coalition, the voting can be different, but the coalition is the same, then they are actually identical voting influence. Okay. Any question about this cooperative gain group decision? Very clear? Yeah. Yes, good. Thank you. Then let's go, to, okay, so the last part here, this is the main part. Okay, so we will discuss about IFN power dynamic. Now, this is my delighted topic. And the slide is in Moodle, so you can check. Okay, so in this topic, we are exploring the concept that will bridge the math and political science. Okay, so similar to group decision making a while ago, but now you want to see the actual power, yeah, not based on who speak louder in the room, yeah, but based on how the system balance itself to survive, yeah, and to check in the long term rather than just short term. This is the whole point of IFN. Okay, so I will discuss several topics in here, and then I will discuss the examples, family, and then discuss more detail the theory, including the centrality topic, and then at the end I will again discuss more on the examples in business and politics. Okay, so we start with what is called strongly connected network. Okay. So everyone have family, right? So okay, if you scan this QR, so you will go to that. What is the? Oh, I think this one. So you will get this power dynamic virtual lab. Okay, this is the. So there are many explanations here that you can read by yourself. Okay. So, and you just go at the end, at the bottom, and start the challenge. Then you will see the lab tool. Okay, there are many examples. Okay, some of these I will discuss in the slide. Okay, so this one, and then you just compute to get the either premium network or cardinal network to get the value of IFN. This is the ideal flow network. Okay, and based on that, you can also compute. Yeah, these are the matrix analysis. If you have this matrix, okay, then you can analyze. For example, you want to get betweenness centrality, then you will get this one, the value. Okay, you just input the matrix, and then you can compute all. Yeah, you can compute closeness, degree centrality, page rank, okay, and so on. Yeah, including band sub index, sub index, and so on. These are the value that you can compute. For example, yeah, you can check who will make a coalition. Yeah. Similarly, after you compute, this is the matrix that you input. Okay, that means the current situation. Yeah. On the right side is the output, which is the ideal flow matrix. So again, you can also compute many different analysis here. Yeah, more than the left one. Okay. Including the all cycles you can get. Yeah. So what is the characteristic of IFN? Yeah. So is in this pattern, you see that the sum of rows is exactly the same as the sum of columns. Yeah, the same pattern. Yeah. So if you press here, wait for a while, you will see the actual values. Okay. So with that, you can also visualize. So the matrix and draw and so on. Okay. So the help file is down there, how to use. Okay, so let's come back to the slide. Yeah, the calculator is there. So in every family, usually you have, you want to create a decision, then the question is who influence who, right? And when there are certain conflict happen, okay, who is the authority in the family? Yeah. So sometimes in the organization or in the country, yeah, or in the business, not necessarily in the family also. Okay, so sometimes the most powerful, okay, is not necessarily the formal authority. Yeah. So this is how you will create the network. Yeah. So say I have a family of father, mother, son, daughter. Okay. So you need to create what is called a strongly connected network. Okay, you need to create strongly connected network. Yeah. So these are example of strongly connected network, meaning from one node, you can go to any other node and come back. Okay. So why we need to deal with strongly connected network? Yeah, because you don't want to have domination in decision power. Yeah, so you don't want to have dictatorship or just dummy. Okay, so you want to have check and balance system. Yeah, so then in that case, you need to create what is called strongly connected network. Yeah, because strongly connected network represent check and balance design topologically. Okay, so be careful when we say dominance here. Yeah, so dominance here refer to whose need and preference that drive the overall direction of the system. Yeah. Say, for example, in business strategy, okay, yeah, in business strategy, the we want customer to be the focus, isn't it? In the politics, democratic, we want the power belong to the people. Okay, so it doesn't mean, yeah, the customer will get free product and then seize control of the company, bank account, and so on, right? So it's just the beneficiary of the system. Is that clear? So the same thing, yeah. the government legitimacy derived from popular consent, yeah, by election, isn't it? So, but it doesn't mean that every single citizen can unilaterally design the budget and make the law. Okay, so the power belong to the people. Okay, but this is represent the needs. Okay, and the preference or the interest. Okay, so this is the example of two part. Yeah, one is called this network is called weakly connected. Yeah, so a weakly connected system have no feedback. Yeah, this is an example. Say in this example, the father is the source node, and the son and the daughter are the sink node. Okay, so they are practically redundant in the system. Yeah, the son and daughter. The father is the source, so become dictator. Yeah, and yeah, the children are the sink, so they are basically redundant. What the meaning of redundant? I can remove these two nodes, okay, and they are still father and mother become a system on itself, yeah, which is strongly connected. Do you understand this, or do you want me to explain more detail about the graph theory before we go here? Probably network representation is better to explain first. Okay, so you can see the plan base. Okay, can you go to model? There is a slide called network representation. Let's go there first so that before we go to power diagram so that you can understand better. Is that okay? Are you ready? Okay, so there. So this is mathematics, okay? And when you take the exam, you will use this notation that usually I put as MATLAB notation, okay? So then I just say list also, yeah? So when you see this notation, you know what to do. Is that okay? The same thing with that calculator a while ago is using this notation. Okay. So we have three representation of a network. Yeah, one is adjacency matrix, second is adjacency list, and the third one is using string. Okay, so this is an example of network. Okay, then you can put that as adjacency list. What is the meaning of adjacency list? It's kind of JSON list. Yeah, so look at this network and look at the adjacency list. I will put A as A to B. Yeah? So the value of the weight is 1, then A colon B. Okay, so this means A to B. There is a link, then I will put this notation. Now this notation is called adjacency list. Is that clear? So now there is a link in here between B to C, then B colon C. Is that clear? Okay, and then the same thing here. There is a link from C to D, right? Then you will say C colon D. Yeah, 1 is the weight of this x. Okay. Same thing with D, go to B, isn't it? Yeah. And E going to two links, yeah, EA and EB. Right? So E in here is the origin. This is the destination. Yeah. EA and then EP. Can you see that? That means the edge. Is there any question about this? This is the notation only. Yeah, this is very useful because this is compact. Yeah, adjacency is very compact compared to matrix. Okay. Yeah. So now you can also have this network, and then you can put it as adjacency list and adjacency matrix. Yeah. So here, so this network is different from a while ago. Yeah, it look like the same but different. Yeah, this network, if you put it as adjacency list, you will have this one. Yeah. So for each link, you will put A, B. Yeah. From here, B going to C and D, right? So you will have B as the origin, and then C and D as the destination. From C going to E. Yeah. There. From D going to nowhere. Then you will see here empty. Can you see that? Okay. And E going to two places, A and B. Yeah, so here. Clear, yeah? So now we can put that into matrix. Okay? So D is a sink node. That means going to nowhere. Yeah. A sink hole. Yeah. When you go there, cannot go out. Okay? So in matrix, you will put A, B, C, D, E. This is the name of the node. Yeah. And then you will put it this way. Yeah. So all the one that have value here, you will put as the value of the edge. Yeah. So in here, all one, so you just put one. Okay. So A to B, one. So A to B, one. Yeah. B to C, and then B to D. So you will see this one and one. Can you see the correspondence between the matrix and the network and the adjacency list? Clear or not? Now, one characteristic of this, the one that I put red here, yeah? If a matrix have a row that is all zeros, that means signal. Clear? Okay. How about this one? Okay. So in Moodle, because I need to put it as text, okay, then we need to use MATLAB notation for the matrix. Okay, something like this. So what you will do, you copy this one and then paste it in text file, and then every semicolon there, you press enter, then you will get the matrix. Clear? Yeah. So when you see that MATLAB notation like this, okay, you look at the semicolon, okay, and then you press enter. And this is actually the one that you input in that calculator, isn't it? Yeah. So how you represent the matrix is very simple. Yeah. Just comma, separate by comma. Yeah. And then semicolon at the end of each row. Clear? Good. So let's practice so that you will practice a little bit. Yeah. Can you, one person send the adjacency list, the other one create the adjacency matrix. Write it there in the Zoom. You can write here. You can use the pen and write there. And you can claim your recitation. Anyone can create adjacency list. And the others create adjacency matrix of this network. it difficult? Easy? Just deduce. Okay. Oh, okay, good. So A to B. Okay, good. Yeah, this is the result. Yeah. So if you look at the matrix, yeah, from adjacent series you cannot see, but from the matrix you can see. Here, can you see this? The fourth column is all zeros. Yeah. So when all the rows, all the elements in a row is actually all zeros, that means sync. No. Yeah. If all the element in one row represent all zeros, that means source node. Yeah. Can you see the value here? The fourth here, D, right? From D can go anywhere but cannot come back to D. That means source node. Clear or not? Yeah. Do you understand the meaning of source and sink now? That I introduced in power dynamic a while ago. Any question? Okay. So, anyone want to throw this? You can throw here. So how many? 1, 2, 3. Okay, I will throw the node and then you throw the link. Is that okay? So I will put A, B. Okay, I will put C here, D, and E. Okay, can anyone help me to throw the network based on that matrix? Just one line at a time. Come on. Yes, A to B, correct. How about this one? What is this meaning? 1, 2, 3. 3 links there. From B to B to C, D, and E. Yeah. So 3 links. Correct. Very good, Lester. And then how about this one? That means from C. C to D. Very good. This one D has nothing. Yeah. So will not go out from D. And then what is this? E. E go to. Very good. Yes. So you get the network. Okay. Easy? Yeah, super. Okay, so I will close this one. Let's go to the next one. So yeah, this is the result. Yeah. Can you notice also D in here is a SIG node. Yeah. You can see also clearly from the adjacency list. Yeah? Okay. How about this one? Can anyone create adjacency matrix? Adjacency list. Which one is easier for you? Adjacency list or adjacency matrix? Yeah, if just small nodes like this, matrix is probably easier. Yeah, but when you have a very big network, okay, adjacency list is faster than the matrix because a lot of zeros in the matrix. Practice. Is there any sync node, source node? Yes. Who is the? Okay, Thomas. A, B, and B to C, correct. And then C to D, okay. And then B to D, okay. B to E. Okay. Yeah. Very good. Okay. And very good. Okay. So clear? No problem, right? Just representation between list and matrix. Okay. So this is the next one. I just skipped this one, yeah. But look at this. This is interesting, yeah. Why this is interesting? Is this strongly connected or not? What is the meaning of strongly connected? Strongly connected means from one node, you can go out from any other node and then come back. Question, is this strongly connected network or not? Yes or no only? No, this is no. Yeah, yeah, Thomas, you're right. Yeah. This is not strongly connected. Can you see this? From D, I can go to C, but I cannot go to A. Right. Okay. This is weakly connected network. Yeah. In fact, this one have two components. I will show you. Yeah. This is the first component. Okay. And this is the second component. Yeah. So from component one, okay. This is second component. Yeah. From component one, this is the component means strongly connected. Okay. A, B, E are strongly connected. That means you can go from A to B and E and then come back. Okay, a component is a sub-network. Okay, so from component one, I can go to component two, but from component two, I cannot come back to component one. So component one is the source component. Component two is the sink component, isn't it? Okay. So transport network cannot be like this, yeah? Yeah, correct? Transport network must be strongly connected, yeah, because otherwise you can go to the mall and then cannot come back to your home. Right, that's not correct. Okay, transport network always strongly connected, yeah. So, okay, next. Oops, I will clean. Okay, strongly connected network. Okay, if there's a path, yeah, from any node to any other node. Okay, so meaning people can go somewhere and then can come back from any node. Is that clear? The meaning of strongly connected. Okay? And in graph theory, this is called strongly connected network. In linear algebra, okay, they have different name. That matrix that creates strongly connected is called irreducible. So they are the same thing, identical. Okay? So when we say an irreducible matrix, that means strongly connected network. Is that okay? Just different name from different field. Okay, so this is an example. Okay, in this network A, this is weakly connected. Why? Because A is a source. Yeah, weakly connected means you have source node, sink node, or sink component, or source component. Yeah, sink component, source component, sink node, and source node. Any of this will create weakly connected network or unconnected. also weekly. Yeah. So this one have source node in A, and D is actually sync, right? So in that case, this is weakly connected. How about this one? This is also weakly connected. You have source here, you have sink there. Okay. How about this one? In fact, this is strongly connected. Yeah. And the flow is balanced. Yeah. Every flow in equal to flow out. This is ideal flow network. Clear? Yeah. So ideal flow network have two requirements. One is strongly connected. Second, the amount of flow in each node must be balanced. Yeah. Equal to flow out. You see here, one going in, two going in, the out is three. So exactly. Yeah? In this node, you have two going in, three going in, out is five. Yeah, in this node, you have five going in, going out is 4 plus 1, so 5 again. Yeah. So the node value represent the sum of this flow in or flow out. Clear? Yeah. Easy, yeah. Okay, so yeah, this is called ideal flow network. Yeah. Two requirement only. First is strongly connected. Second, the flow must be balanced. Okay, so component is called subnetwork, strongly connected. Subnetwork is called component. So if you look at this is strongly connected network A, because I can go from A to D and then come back to A. Yeah, and from any node I can go anywhere and then come back. Right. So this is strongly connected. How about this one? This is unconnected. Yeah. And this one is weakly connected. Why? This is from this component CED. Yeah, this is the source component, can go to the sink component here, A, B, F. Yeah, but cannot come back. So this is weakly connected. Okay. So the two of them, unconnected and weakly connected, is called reducible in the matrix. Okay. So how about this one? Can you find the component? A, B, E is a component or not? Yes. How about this one? B, C, D is a component. How about the whole things? Yeah. So subset can be the whole set, right? Subnetwork can be the whole one. So can I go from C, go to E, A? Yes, can go. So in that case, we have three. Yeah. Yeah. So this part is component, this one is component, the whole thing is also component. Very good. Yeah. Clear, yeah? Okay, good. Let's go to the next one. Yeah. So this is the answer. How about this one? Two component, yeah. Okay. Sink and node component. Yeah. So D and C create a component, right? Strongly connected. And then A, B, and E create a component strongly connected. Yeah. How about this one? Look like the same, but not the same. Yeah? This is like a kindergarten. In the kindergarten, you look at the which one is similar, which one is different, right? So, so can you find the sink component? Yes, correct. Yeah, BCD is a sink component. Yeah, in that case, A, B, E is the source, right? Good. Yes. How about this one? Can you find the source? Can you find the source component? It's a component. It must be strongly connected, meaning from that node can go anywhere within that component. Which one is the source component? Correct. Yeah, A, B, and E is the source component. Yes. How about this one? Can you identify the sync node and then the source component? Sync node is T, correct? How about the source component? No. Yes, 4. Okay, not just PCE, yeah, but the whole things here. Yeah, A, B, C, E, yeah, is a component of its own. Yeah, very good. Clear, yeah? How about this one? Can you identify the source node and the sync component? Simple practice, yeah, so that you can master this network diagram. Yes, T is the source node, very good. How about the sync component? Yeah, the whole things. Yeah, very good. Yeah, the whole thing is the A, B, C, E is the sync component. Yeah, very good. How about this one? Yeah, last this one. Yeah, this has been identified. Yeah, the component there. Yeah, there are 3 components that you can put. Actually, this one CT is also component. Yeah, TH is also component, right? If you want. Yeah. So from this left side, yeah, A, B, E, right? So can go there, but cannot come back, isn't it? Oh. Yeah, this is the source, correct? And which one is the sink? This one, yeah? F and G is the sink. Yes, very good. So you master this already. Super. Okay, so let's close this slide. Come back to power dynamic. So now, is it clear? Yeah, the father is becoming the source node. And I can, so source node or source component, practically the dominant, okay? So they can remove all the others, then the only one in the system, okay? This represents dictatorship, yeah. Well, redundant, the sink, yeah, like the son and daughter here. So they can be removed. So that's why they are redundant. Clear? Okay, so when you want to create IFN, you should not make like this. Yeah, must be strongly connected. Yeah. Why? Because you want to create system that has feedback system, that is check and balance system. Okay, not dictatorship and no redundancy. Okay, how about this one? This is incomplete. Yeah, the one that if you see there is a network that is actually not strongly connected. Yeah, still have sink and source node or component. Okay, they represent incomplete system. Yeah, there is no check and balance in this system. So if you want to create a check and balance, then there must be certain. For example, from here you come back to the management. Yeah, so there is a feedback. Yeah, maybe through survey and so on. Okay, then there is a check and balance. Okay. Hey, what happened? I cannot remove. Okay. Yes. So this is not okay. Yeah. So this represent again in the project management. You have the owner, you have the contractor, Okay, the owner represent the source node, contractor represent the sink node. So this is a node check and balance. So not strongly connected. Okay, so don't do this. Okay. Next. So the same thing here. Say you expand the contractor, okay, consists of design consultant, supervising consultant, and the worker. Again, still incomplete system. Yeah. So not the amount of number of nodes, okay, but the interconnectivity in the network matters. Okay, so don't do this also. So how to make it strongly connected? How to make it strong? So if you have like this, one way is just to make a two-way communication. Okay, so I just put up arrow, then you have strongly connected already, isn't it? Easy? Yeah. So this is okay. Yeah, the right part is okay. Yeah, the left side is not. Okay. So uh sometimes, okay, if you look at this system, yeah, this is incomplete, this is already irreducible, so strongly connected. Okay. There is something there in that system that actually still hidden from this system. What is that? Still incomplete actually. If you have this owner and contractor, yeah, yes, this is already strongly connected, but there is one problem there. What? The target, the beneficiary of this system is unclear. Okay, so you need to add probably the building itself, right? So you can make strongly connected simply by adding link two-way communication. This is one way of technique. Yeah. Another way is actually to add node, yeah, which is the target, yeah, the output of the node. So in this example, the building itself you can include, yeah, in the system. Yeah. With that, that building will become a feedback to the owner, isn't it? Yeah, so you can add node, and then you can create a feedback. Clear, yeah? The technique to create strongly connected. Yeah. So either you add two-way communication or adding link or adding node. That's a simplified method to do. Yeah. Okay. So once you have the irreducible or strongly connected, yeah, then you can start to put this into matrix and then put into calculator. Is that clear? Yeah. Once you put into calculator, you can calculate the power. Yeah. So this is the input that you need. For IFN power dynamic, the input is a network that you see inside the system. So if your network is still not strongly connected, yeah, that means still weakly or unconnected. That means you still need to search, yeah, for other node or other links because incomplete system. Is it clear? Okay, let's give the example, okay, of family power dynamic. Yeah. So question is here. I want to capture the relationship in within a small family between mother, father, son, and daughter. So everyone have family. So this is something that you are familiar. Okay. So I want to. This is not okay because these two networks are weakly connected. So we should not use this one. But the middle one is okay, right? So this is strongly connected. Is it clear? The input must be strongly connected network. Okay, let's see. What you will do is to input the network as capacity matrix. Yeah. And then when you input this network, you compute the ideal flow. Okay. You will get that value in the right. Okay. And when you get this value on the right, the ideal flow, okay, then you see the power on the sum here. This is the node value represent the power. Very simple. You will see that is father, mother, son, and daughter. So you will see that the mother, son, and daughter in this network have equal power. Yeah, and father is the weakest. Yeah, because one and the other is two. Okay. Okay. So this is the basics. Yeah, the base scenario. Okay. So then, what if now you can simulate, right? The scenario you can simulate. What if now we have a new, say, house cleaner? Yeah, this red one. Yeah, and this house cleaner make a good relationship with the daughter. Yeah, good friendship. Of course, the mother is the one that influenced the house cleaner. Yeah, good relationship mean you have two-way communication, isn't it? Okay, so input this network into the capacity matrix, 0 and 1, right? And what happened? Yeah, so compute the IFN. Oh, in this new scenario, with the house cleaner here, the daughter power become the highest in the family. 4. The father, this is funny, the father has even lower power than the house cleaner. Yeah, in this family. So the assistant of the house cleaner who make good friendship with the daughter, yeah, change the balance of power within this family. Okay, and the mother and the son have the same power, 3 and 3. Yeah, 3 times than the father. Clear, yeah? Okay. So what happened? Oh, say the father learns about power dynamics, yeah, the management. Okay. Now what happened if the father want to influence everyone in the family? So I can put red one here. Can you see that? Eh? So we make a new scenario. I want to say so father make a new influence to all. Yeah. He want to become more powerful, isn't it? Yeah. So question. Will his power become the most dominant? Yes or no? Yeah. So then you check the in the long term what will happen. Yeah. You calculate the IFN. You can predict his power based on this structure. Interesting, right? Okay. So you can predict based on structure alone. That's interesting. Yeah. So there I include that. Yeah. 0 and 1 in the capacity matrix. And now the cardinal network become this value. So that easy to compute the power. Okay, I just divide this sum, okay, with the minimum. Yeah, so the minimum is 3 here, right? Okay, so then this minimum become 1. Then you can see the power compared to the others, compared to the weakest. Yeah. So the house cleaner is the weakest now in this scenario 3 and 1. And the father only improved the power just 30%. Yeah. Compared to the house cleaner. Yeah. He is still not dominant, even though he influenced everybody. So can you see this structure matter? Yeah. So is it interesting that you can actually predict what happened within the structure. Yeah. Don't believe me, you can check your own family, something that you're familiar within your own office mate, who influence whom. Okay, within your own community that you have, organization, or within the country. Okay, then you can start to check, yeah, and you can analyze their power, who influence others, and so on. And more than that, okay, if you look at the IFN power dynamic down there, there is a analysis, right? Matrix analysis. Then you can see the signature. Yeah, this signature represent the cycle. Yeah, this is represent the cycle analysis. Yeah, because the computation of IFN, yeah, is based on the minimum cycles. Okay, to be redistributed among this. Yeah? So this is a little bit different from between the centrality or Markov centrality because discrete. Yeah? So the probability is the same as Markov centrality, but the computation is based on cycles. Okay, so then you will see the pivot. That means between these cycles, which one is actually connected together? They go together. Yeah, that's represent the further analysis if you want. Yeah. So in this story, yeah, the father can influence everybody in the family, but only have a little bit more power than the house cleaner. Yes. Yeah. Okay. So what's the lesson of this family A? Yeah. Having more influence to many people does not mean that you will become dominant. Okay. So the dominant structure you still need to compute, yeah, and depend on the network structure, you know. And of course, later it depends on the strength of influence, yeah, not the number of influence. Yeah, this is very important lesson, yeah, from power dynamic. Okay, so say if you compute this IFN, say example, you get a value of this, then how to get the actual power? Yeah? Power is basically relative to the others. So in that case, you just divide by the minimum. Say in here, the minimum is 58, right? So then the power become 1. And the others, now you will see, oh, this one, the mother is just almost 3 times. Yeah. Then the daughter is just 2 times. Yeah. The son is just 1.6. Yeah. So 60% more influence than the father. This is based on cardinal network. Yeah. Yeah. Cardinal network is computed based on the strength of influence. Premier network is computed based on the network structure alone. That's the difference between the two. Okay. So this is another scenario. Let's call this family B. Yeah, a while ago was family A. Okay. So say you have two capacity matrix, C1 and C2. Yeah, this is C1 and this is C2. Okay. So capacity matrix means the current influence. Okay. So you just put the influence value that you can put there. Okay. The ideal flow means the ideal, that means the steady state. Okay. Long-term solution, not just the current. Yeah. We are not interested with the current solution. We interested if this happen long time, what will happen? That's called steady state solution. And that's basically the IFN. Okay. So this red arrow here represented by this 2, 1 here. Is that okay? That means initially the father and son do not have communication. Okay, and in the second scenario, the father and son communication is repaired. What will happen? Yeah, to compare these two scenarios, what will happen to the power so that you will see. Yeah, and then if you can connect to game theory, you will see uh, whose benefit. Yeah. So if you compute based on Premier network, okay, because Premier network will compute exactly just 111. Okay, so the power is exactly the same. Yeah, because they are strongly connected. So C1 and C2 have exactly the same Premier network. Yeah, the power in here C2 have equal power. But when you calculate based on the actual influence, yeah, so 1, 2, 3 in here, okay, then you will see the actual power varies, yeah. So mother is the most dominant here, okay, and when it improve the communication, yeah, this value, yeah, so the strength of the sun, yeah, is actually get higher. Yeah. So that means the communication between the father and the mother, between the father and the son, actually benefit the son more than the father. Yeah. So then you can connect to game theory. Yeah. So that's represent the utility value. Yeah. Who's get more benefit? Okay. So then again, you can compute the relative power. Yeah. So if you compare to the F1, the scenario without communication. Yeah, can you see? This is without communication between father and son. Yeah, so the father is still the weakest. Yeah, and then the son is 1.59. Okay, and here going up. Yeah, so the son influence now become 40. Yeah, so now the son and daughter become have the same influence, the same power in the family. Yeah. Before the son less than the daughter. Yeah. But when the communication repair, the son and daughter have the same power. Is that okay? So based on that value, you can start to interpret, what's the meaning of this? Yeah. So what's the lesson we have here? So when you improve the communication, yeah, actually it will increase the balance of power, yeah, and reduce the power domination of the others. Okay. And cardinal network will help you, yeah, to show the actual power based on the actual influence. Yeah. Premier network is based on structure. Is that okay? So yeah, this one, this is a difficult to explain. The father of this family B, okay, want to take control. Suppose, yeah, he want to take control, become dominant. Or earlier was one, right? His power is one. So what happened if he want to take control? And then he simulate this value. Okay, so what happened if my influence is actually 4? Yeah. In order to make him the most powerful in the family, then he need to change the value here to become 4. Yeah, on the surface, of course, there is no problem structurally. Premier network still the same, yeah. But because we change the capacity matrix with the strength of influence, then we need to compute cardinal network, yeah. So when you have the cardinal network, yeah, with this value, okay, then yes, the father become the most dominant. Yeah, the mother become the second dominant, and the son and daughter have the same equal value. Look like ideal, isn't it? Huh? But there's a problem there, yeah? What is the meaning of this 4? That's the problem there, right? the meaning of this 4 means, so you probably want to see the potential problem. Yeah, that means the children now dependent more on the father than the mother. Yeah. So the change of the father who want to take control may lead to competition between the father and mother. So become a power struggle within the family. Can you see that? So this is unhealthy competition. Yeah, that means the parent may maybe spoil the children and so on. So in that case, if you want to base it on love, then you probably don't want to take control at all as a father in this example. Yeah. So do you understand the application of power dynamics? Okay, you have the network of the situation that you currently have. Okay, based on network structure alone, and then you can set the influence, the strength of influence between one person and the others, or between one organization and the other organization, and the stakeholders, and then you compute that, and then you can get the power, and then you can interpret that power. You can predict what will happen if I change this, what will happen if I change that. That's the dynamic there. Very interesting. Yeah, it's a very powerful tool. Okay, so now I want to go to the theory so that you will understand better. Okay, so what is IFN? Yeah, so why the name is ideal flow? So ideal flow represent ideal condition. Yeah, so the story about IFN is the story in heaven. Okay, it's talking about ideal things that they are ideal, that within our reach. Okay, so the Bible said things about things in heaven, yeah, not things on earth, right? So that's why I created this, yeah. Yes, George.
Sir, sorry to ask, but is the strength of influencer usually a subjective value? Like,
Yeah, I will discuss
so
that
it's
later. There is two possibility, yeah. One is subjective value that you use Delphi method. Okay. The other one is you translate that based on the data. Okay. Then you can translate that into real value. Okay. We can discuss that later, more detail, yeah. So, but that's good question, George. Thank you. So ideal flow represents something ideal, ideal condition. Okay. Then you ask, why? Why we need the ideal condition? Because ideal condition represent the ideal goal, right? Without knowing what is the ideal things, okay, then you don't have direction. Okay. So by having the ideal goal, okay, then you have effectiveness. Yes, you can create using IFN prioritization, you can create efficiency. Using ASP, you can create efficiency. Yeah, efficient. So, okay, you work very hard, you get certain efficiency. Yeah, but that is not necessarily effective. Effective means you have the goal and you reach the goal or close to the goal. Okay, which one more important, effective or efficient? Of course, effective more important than efficiency. Okay, so by knowing the goal, it will guide you toward effectiveness. Okay, so IFN analysis will give you compass, give you what is the ideal direction to go in the policy, in the society. Yeah. Based on that goal, you have the direction to go. Is that okay? Yeah, that's why we need this, because this will give you certain ideal condition. Yeah. So then you say, but I cannot reach that goal. That's fine. Okay. As long as you continue in this direction, eventually you will reach that goal, right? Okay. So the direction is more important than uh, just doing it, yeah, for the sake of doing it, isn't it? So once you have the right direction, then you can create the efficiency. Yeah. But if you just improve the efficiency, but you go to different direction, not in the right direction, then it just go nowhere. Okay. So, okay, then let's go to the detail now. What is IFN? I mentioned a while ago. Okay. So IFN is basically irreducible premagic. Yeah. So by definition, this is a steady state, okay, relative flow distribution, okay, in a strongly connected network where the flow are conserved. Yeah. So you have strongly connected, that means irreducible. You have conservation of the flow, that means premagic. Yeah. So in a sense, yeah, IFN is integrated balance equilibrium. Okay. So in the matrix, we said irreducible premagic. Yeah. In the network, we said this is uh, strongly connected, yeah, and conservation of the flow. Is that clear? Yeah. So next. Okay. For IFN, okay, you have the capacity matrix and then you compute the ideal flow. Capacity matrix represent the capacity of the road network. So IFN was initially created for transportation. Yeah, that's why the jargon is transportation. Yeah, capacity, congestion, and so on. Okay, so but we can apply this to any other application. Yeah, besides transportation. So for simplicity, I want to introduce you with two integer, yeah, type of ideal flow. Yeah. Let's call this first premier network. The second is cardinal network. The first one represents the structural influence. Okay. The input is just 0 and 1, who you are linked to. Okay. When you want to get cardinal network, okay, you need to input not just who you are linked to, but you also put the value of the strength of influence. Okay, if you don't have this strength of influence, then all you can get is only premier network. Okay. Okay, so this is example of the C, yeah, the capacity matrix, and then this one is the example of premier network, and this is the example of cardinal network. Okay. Can you see this? Yeah. The premier network is not 0 and 1. Yeah. So this is represent the number of minimum cycles, yeah, in order to create that ideal flow. Ideal flow means this is strongly connected and premagic. Can you see this is premagic? 3312. This one also 3312. Okay. Okay. This one also, you see, this is 25, 25, 12, 15. 25, 25, 12, 15. This is also premagic. What's the difference? Yeah. In Premier Network, you get the minimum cycles in order to create that network topology. Okay. In Cardinal Network, you are not just to get topology, you also get exactly the same probability distribution. Look at this. This one is 2 and 3. Okay. Look at this, 10 and 15. Exactly 2 and 3. Right. Huh? This one is 5. So this is, okay. This one is 2 and 8. Yeah. What's the probability? This one 3 and 12. See, like 4 times, right? So exact probability. So cardinal network is not just the network topology, it also represent the probability that is invariant. Can you see that? No. Okay? So the mindset is this, yeah. So if you want to use IFN, yeah, it's more than just the mathematics, yeah. You look at the loops, the cycle, yeah, between the nodes and the links, and then you see the balance. Okay. So irreducible and premagic. Irreducible means strongly connected. What's that mean? That means integrated. Okay? Unity. Right? Premagic, the balance of the flow. Yeah. That is the pattern of reciprocity. Yeah. Justice, fairness, interdependency. So we can create actually, yeah, morality and spirituality based on mathematics, based on the IFN. Okay, and because the network is irreducible or strongly connected, that means you can create based on cycles. Yeah, the karma, basically. Yeah, what flow in must what flow out must flow in. Yeah, so what you give, yeah, eventually will return to you. That's the basic idea of IFN, yeah, which is also in the Bible, yeah. This is in Ecclesiastes. So, yeah, I already explained this one. So this one I have for computation, okay. In the past we have what is called integral. This is also similar integer IFN, okay. But the stochastic is just approximation. So anyway, we don't use in power dynamic at this point. Yeah, I just skip this one. Yeah, this is the example of the value if you have the capacity matrix like this. Yeah. Okay. And this is the stochastic matrix, mean you divide by the sum of the row. 1 plus 8 plus 10 plus 19. So this is 1 over 19, 8 over 19. So this is stochastic matrix. Then from there you can compute the cardinal network integral and the premiere. Yeah. So the cardinal network in here become non-integer. Yeah. So that's why. Oh no, see this is this is the cardinal network. Still integer, sorry. So and then integral network is almost similar stochastic matrix, but not the same. Yeah, it's not the same. This is 7 over 18. Yeah. So while the cardinal network is surely the same stochastic matrix, yeah, as the original capacity matrix, while the premium network is just based on structure, yeah, the minimum number of cycles. So, and these are the cycles that create that network. Okay, these are the cycles that create that network. So remember in the beginning I said you can represent the network as either adjacency matrix, adjacency list, or string. So these are the strings of the network. Yeah, it based on the cycles. Yeah. Okay, and the relative power is just the sum of row or the sum of column because this is the same. Yeah. So and then divide by the minimum, right? So you get the relative power. Yeah. So how many times the power compared to the lowest? Okay. So why you want to get the relative power? Yeah. So there are sometimes, yeah, you change the dynamic structure. Okay. When you simulate the network, okay. So then if you look at only the RAM, yeah, they may have the same RAM. Okay, but actually the power reduce or increase. So in that case, you don't just see the numbers, but you see the actual relative power. Yeah, this is useful. Now come back to what Andrew was talking about a while ago, network centrality. Yeah. So just in brief, I have put there in the calculator, power dynamic, yeah, several centrality measure, yeah. That represent the importance or the influence of the node within the network. Yeah, over time, there are many different proposals on how to measure the importance, yeah, of the influence of the network. So one of them is called degree centrality. That means how many number of direct connection. Yeah, but this will ignore the indirect connection. The second one is betweenness centrality. That means it will compute the shortest path, yeah, between other nodes that pass to each node. And the computation is what a lot reduced. Yeah. And then there is also closeness centrality. Yeah. This one again using shortest path, but take the average shortest path. Yeah, from one node to any other node. Yeah. Eigenvector is based on the influence of that neighbor, and then you compute the matrix eigenvector. Yeah. There is also what is called Markov centrality. So again, you compute similar to eigenvector. Okay. Basically, the three of them, yeah. Eigenvector, Markov centrality, and relative IFN is almost the same value. Yeah. In terms of the probability. Yeah. If you just compute the probability, they are almost the same. Yeah. But the value are not the same. Yeah. And the concept is not the same. Yeah. IFN is based on cycles. Yeah. Markov is based on eigenvector. Yeah. So this is the comparison between betweenness centrality and Markov centrality. Okay, this is the most common centrality that used. Okay, so these are the strength and limitation. One is based on shortest path, and the other one is based on long-term probability. Yeah? So IFN is basically Markov centrality, no? But in relative term. Okay. So the engine, how I compute that? Okay. So I use what is called set cover algorithm. So we want to find the minimum set of the cycle that will cover the whole network. Yeah. And unfortunately, set cover algorithm is well known to be and be complete. That's been exponential. Yeah. Depending on the number of nodes. That's why we can only probably deal with only 15, 10 to 15, less than 10 of the nodes, yeah, if you want to compute power dynamic. If you get more than that, it's probably half or a snap. Okay, so, well, this is the limitation. So, yes, this is very powerful technique, but at the same time, computationally, at this point of time, still not that good yet. Yeah, so probably when quantum computing come up, then this can be solved, yeah, algorithmically. So, but at this point, please bear with me. This is the best algorithm we can find. Okay. Okay. So the result is actually resource distribution endurance. Yeah. So it's a long-term process that you can see very powerful way to get the cycle, minimum cycle. Okay. So now go to what George was asking. So how to do this step by steps. Okay, so I draw the diagram here. I hope this is useful for you. So we start here. Okay, so you identify the nodes. The node can be actor, can be factor, can be strategy, can be role, and not necessarily human, not necessarily agent, can be factor. Okay, and then you identify the links. Okay, and you can, if you have the data, you can check the string of influence on that link. Yeah, so you can either put 1 to 5 or 1 to 9. This is just to simplify. Otherwise, you can put any number. So the most important is you create a strongly connected network. If not, yeah, if still weakly connected, then you come back. Yeah, identify the node and the links. Now this is a loop. Okay, this is the loop. Okay, a feedback loop. In order to create, the first step is to create a strongly connected network. Once you have the strongly connected network, you create the matrix. Yeah, easy, right? You have the network, you can get the capacity matrix. Yeah. So then check. Yeah, you have the strength of influence or not. Yeah? If you don't have, then it's binary, right? So 0 and 1. So in that case, you get the primary network. Yeah, primary network. But if you have the strength of influence, then you can compute the cardinal network. Yeah? From these two, you can get the power. This is one scenario. Clear, yeah? Okay. So the steps. Yeah, I just simplified into 5 steps. Yeah, so number 1, you define the target beneficiary. Okay, so which node can be, say, in the country, usually citizen, right? In the business, usually customer, in the app, usually user, isn't it? So who's supposed to be the target beneficiary of the system that you are investigating? Okay, so identify the target node that the system need to serve. Yeah, and then check the connectivity. Yeah, you get the strongly connected network. Yeah, no sink, no source. Yeah, node or component, and then you get the rate of influence, the data. Okay, represent the strength of network, and stop. And then from there, this is the input, right? So you input it into calculator. If you don't want to use calculator, you just do it by yourself. You calculate by yourself. You can. If small network, yeah, but very big network is very complicated. Okay, so to get the steady state, yeah, where the inflow equal the outflow, yeah, then you get the integer representation of this IFN, yeah, either a premium network or a cardinal network. After that, what you will do? You check, yeah. Remember, the step 1, you set the target beneficiary of the system. Is this target is actually the most powerful? Yeah, that's what you want, right? But if not, then something problematic. Yeah, then you need to shift the balance of the influence. Yeah. Probably you want to add more node, you change the links or the influence. Yeah, these 3 possibility. Yeah. So the goal is to align your structural power, yeah, to the true beneficiary of the system. Okay. So in the flow chart, yeah. So again, you identify the real target beneficiary. Okay, and then you create the network, yeah, with that target as one node, yeah, and then check whether this is strongly connected or not. Okay, if not, then you add node, you add links. Yeah? If yes, then you set the strength of influence, right? And then you compute the IFN, yeah, to get the steady state solution. Okay, so and these are the 2 possible IFN, yeah? Primary network or cardinal network, and then you simulate, right? So is this the target is the most powerful node? If yes, then finish. Yeah, if not, then you change the network structure or the change of influence, then return as a feedback loop here. Okay, you see, yeah. So I hope this is clear enough. Okay, let's go more detail. Okay, so who is the real target beneficiary? Yeah, every system usually have certain target beneficiary. Yeah, so the customer, the citizen, the apps. Yeah, so if the system is healthy, the goal is this must be the most powerful structurally. Yeah, so then you check, yeah, if this is strongly connected or not. Yeah. If not strongly connected, that means there is no system accountability, not checks and balance. There is some dictatorship, there are certain redundancy. So that is not good. Or the system is still incomplete. So you must recurs, yeah, to make it strongly connected, yeah. And then this is the main data collection, right? Yeah. So you have the strength of influence, okay? So you can have the value, say 1 to 5 or 1 to 9. Basically, small, this is the rubric that we can use if you want. Yeah, so 1 and 2 mean very small influence. Yeah, 3 mean certain stronger. Yeah, 5 or 6 mean operational. Yeah, 7, 8 means strategic, and 9 means existential. Yeah, maybe your certain veto power and so on. Okay. So yeah, I can put 1 to 5 or 1 to 9. Okay, this is ordinal scale. So this represents how critical a link to the system success or integrity. Yeah. So of course, higher mean better, more critical. Okay. But be careful, essentiality of this strength of influence does not mean frequency. Yeah. They are not the same as frequency. So this is the common mistake. They use frequency as essentiality. So this is not the same thing. So don't use frequency, yeah, use essentiality. Okay. So this is example, yeah. So a link can be highly essential but low frequency, right? So for example, only once per quarter. So for example, the editor, yeah, auditor, yeah, or moderately essential but high frequency. That they are not the same, yeah. Essentiality and frequency are not the same. So what we want is essentiality, not frequency. Okay. So then, how to gather the data? Yeah, this is I answered a while ago. So you create based on subjective opinion. In that case, you can use Delphi method that we practiced a while ago. Okay, and independent anonymous survey with several rounds. Okay, or you can actually get the actual metric data, okay, and then you map that into ordinal. Yeah, from ratio data to ordinal is very easy, right? You just map the values. Yeah, and important things here, when you have the actual data, yeah, don't use average. Okay, average is bias usually. So you always use median, yeah, and don't use standard deviation. Yeah, always use interquartile range because these two are robust. Okay. What's the meaning of bias? Bias means one outlier will pull, yeah, the average away from the actual central tendency. Okay, that's why always use median and IQR, yeah, interquartile range. Okay, so with that, what kind of data you can get for your own group project, for example, to observe the strength of influence? Yes, you can use opinion, your own, yeah, if it is within your own family. Okay. You can also use the actual data, yeah, to map this. Okay. Any discussion you want to say about this? Okay, so if not, you just use that calculator, yeah, and compute the steady state solution, yeah, IFN, yeah, either area or cardinal network, and then you test, yeah, whether this target beneficiary has the highest value or not. Okay, if not, then you need to change the system, yeah. So I give you an example in business if you want. So this is example of business B. Okay, that in the calculator you have that scenario. Okay, so the business B decided, the board decided that customer must be the most powerful. Yeah, and there is a check and balance system already. Okay. So the question is, which one is better? Yeah, direct feedback or indirect feedback? Yeah. Imagine the board represents the president. These are your minister or the secretary, and these are the department, right? The customer represents the citizen. It's the same thing, right? So question is, which one is better? Compare these two. Yeah. And what will be the influence, the control, and the feedback? Yeah. We can put this into a capacity matrix, yeah, just 0 and 1, or you can have string of influence. So, okay, you can access the tutorial. Or, okay, what will happen if we do that? Yeah. So here in this left part, the board and the management get direct feedback from the customer, yeah, not from the marketing. Then the right side here, there is a feedback from the marketing, okay, or the sales department. And look at this, the value. Yeah. So with the star here represent the premier network. Yeah. So you see here the influence. Yeah, I put the A, B, C based on this color. Can you see that? Yeah. So with direct feedback, who is the most powerful? C. Yeah, customer. Yeah. Without direct feedback, with indirect feedback, who is the most powerful? A and E. A mean management, E mean the marketing. Yeah. So you can see the power shift. Okay. So your system matters. And now I will show you in this example of power dynamic, yeah, not only game theory that we discussed, you can start to see that the network matter, the network structure matter, how you influence others, yeah, matters in the system. How you get the feedback matters. Okay, and this is an example of 4 scenario in the office. Yeah, so this is the best case like a while ago. This one, because this is the best, right? A while ago. So then, what happened if, okay, now there are 3 additional scenario. Yeah, one is the production influence the marketing. So the marketing must obey what the production department say, or the marketing is actually telling the production, or there is a two-way communication between the two. You first may guess, okay? Probably the two-way communication better, isn't it? All right? Okay, but when you compute, when you compute the 4 scenario in terms of premier network, this is the base scenario. Okay, the management and the sales, yeah, get the second highest important. The production is also important. Yeah, this one C is the customer, right? So look at the value A and E. Yeah. A is the management, E is the sales. Yeah. But when you put this two-way communication, yeah, the power of the sales is now become very powerful as high as the customer. Yeah. The production become as important as the management. Okay. And actually the best one is this one, yeah. The marketing influence the production. Yeah, so that you will have the balance of power here. Can you see that? Yeah. So if you make the production higher than the marketing, then again this is unexpected. Yeah, when production department actually influence the marketing actually get higher power. Yeah. That's interesting to notice. So by looking at this scenario and look at the power balance, and then you start to see and you start to interpret. Yeah. Okay. So yeah. So in politics, you have trias political based on Montesquieu. So there is a executive, legislative, and judicative. And here I I simulated how if the change, the strength of influence not the same. Yeah? Then you will have a different value. Yeah. So executive become stronger. Yeah. So the cardinal rocks show that if the legislative branch write a law granting more influence to the executive, yeah, then the executive mathematically become dominant power in the long run. Yeah. Even if the structure, agreement network, yeah, equal. Yeah. So I hope this is useful lesson for you. Yeah. This is just a summary. You can read by yourself. So that using this simple technique, yeah, it's a very simple quantitative number. So you can predict, you can simulate, and you can control. Yeah. So 3 level of understanding in the science is there. Okay. So I hope this is you can use in your group project. So is there any question? What did you learn today? Any feedback? Yeah. Yes. Yes, please, Andrew.
Hello, sir.
Yes.
I was thinking it's already 9, so maybe
Okay.
if they don't want to
Yeah,
prolong.
okay. So,
But I'd like to ask some question after, if
okay.
okay. So
So, yeah, thank you very much for today. So you can dismiss. Yeah. Thank you very much. Yes. I hope this is
sir,
interesting. Yes. Oh,
uh,
very useful. Thank you. Yes. So I hope you can use, okay, in your group project. Very simple.
Thank you, sir. Bye,
Yes.
sir.
Yes, bye-bye.
sir. Hello
Yes.
po.
Okay. Go ahead.
Okay. I just ask some clarifications. By Premier Network, you mentioned. Wait, I'll get my notes first.
Okay.
You, you mentioned you can know how many steps
Steps.
to get into the IFN. Or is it? Wait.
The cycles. You
Yes, the cycles. I mean
Yes, you can.
So,
Yes. So I will show you if you want. Wait, I will skip this one. Don't keep this chart. Okay. Wait. Oh, okay. Can you see the calculator here?
yes.
Okay. And then you can get the cycles. Oh, where is the cycle? Yeah, netbox signature. There. This represents the cycle.
How does it do that? Maybe that's the question.
Okay. Yeah, okay. So I have a playground here. This one is also there in Moodle. So you can, and in Moodle, in fact, I have games so that you can understand how it get there. Oh, well, maybe this one. Yeah, so this is the matrix, and then you want to get the cycles based on this game. So you can create. So you click this one. Oh, from A to C, right? And then from C to B. From B to, say, to A again. Oh, no. I'm sorry. This one is from A to C, C to B, and then from B to A. There, I create a cycle.
Sir, can you clarify what is happening here. What does a cycle mean, or
Oh,
uh
oh, okay.
okay,
Can you see this? If
okay,
I go from, can you see this network? If
yes,
I go from A to C and then to D and then to B and then come back to A, that is one
it's a
cycle.
cycle. Okay,
Okay? And
so
then,
it's
yes, and then I delete that. Okay? And then the
okay.
remaining still have this one, right? So then this one going here and then going back. That means one cycle. So that's why become, what is the cycle available?
The
This one. See?
okay,
Correct, yeah?
yes,
Yes.
sir. I'd like to clarify too,
Uh-huh.
since you mentioned a capacity matrix
Hmm,
becomes is the current state and IFN is the steady state.
correct.
And to get to IFN, you need cycles,
Yeah, you need, the algorithm will compute the minimum cycles.
the minimum cycle.
Okay, so here, this is the, why cycle? That's the question, no? Because you want to distribute the, for example, your government, yeah? So without the cycles, you use between the centrality, then the government is the most powerful, correct?
Mm.
But that's not what you want. You want the system beneficiary, which is the citizens, to be the most powerful, not the government, right? So in that case, we want to know how to create that kind of system. So this is based on the cycle, then you will see. Okay.
Is a cycle like reducing,
Distribution of resources. Cycle means distribution of resources. The flow represents the resources in the system.
but wait, so is a capacity matrix irreducible?
Yes, must be reducible.
It must be.
Must be. You can check. So you can check here. Is reducible? Yes.
Okay.
Okay. So is this pre-magic? No, yeah. So capacity matrix is irreducible but not pre-magic. Okay, but this one is always irreducible
Okay.
and always pre-magic. Yeah, that's the difference, right? So when in the steady state, okay, then of course the influence they are influencing each other, so then become pre-magic.
So IFN just is a change in the intensity of influence.
Correct.
Okay, okay.
Correct. You are very smart.
Then, sir,
Because the
you
influence long term, yeah, this one is influence short term. Yeah,
mm,
capacity is the influence short term,
okay,
current condition, right? So you're not interested with the current situation because current situation always change,
always
right?
yes.
So you are interested with certain that steady state condition with this long term. What will happen if this condition continue again and again? That is the ideal flow network.
How do we conceptualize that change? Is that part of the computation?
Which
We mentioned how
which change you are talking about?
the recent one, the the capacity matrix defines the structure, and at some point the steady state will be the ideal flow network. How does the capacity network turn into the IFN, or the steady state network?
Okay, that
Is
very
that
long.
like a proposal? Is that like
No, no,
or-
no, no. Uh, so I have one whole book about ideal flow network that you can check.
yes.
Actually, I have also I put it there here.
Yes.
I think like 600 pages book. Yeah. Also in Springer, right? Nature is published. So okay. If you want to see, you can go here. Index. Okay. This IFN virtual lab, actually step by step. I'm telling how do you compute IFN.
Maybe just the concepts are not the actual computation. Where does the transformation of the capacity
Yes,
uh
this is the
do it?
concept. So you have first this one. From capacity, you compute the stochastic matrix.
Maybe
So this one, look at this. 5, 1, 1, 2. The sum is how much? The sum is 9,
9, yes.
right? That means this one become 9 over, this is not that good. 1, let's try one. So yeah, the computation of the fraction is not that good. This one must be 5 over 9, 1 over 9, 1 over 9, 2 over 9. Okay? This one is 1, so this one must be 1. This one is 2 and 2, that must be 50%. See? 0.5, 0.5.
Maybe the question is, sir, let's make an analogy. The capacity matrix, let's say that's maybe for our group.
Okay, so let's say in transportation so that you can get the idea.
Yes, yes.
So there, yeah. So
Yeah.
capacity matrix means the number of lanes.
The existing number of lanes.
Existing number of lanes. Yeah.
Yes.
So stochastic matrix means the probability to turn left and right and to go straight or
Okay.
U-turn.
It's like a description of the existing.
Existing. Okay. And then ideal flow means how much is the flow? In fact, we can see here if you look at this. Okay, if you go here in the application, there is IFN transport. Even in the intersection, if you want, you can go. There in the intersection design. Okay, so you can actually get the optimal cycle timing and so on. So you can get the the phase and so on based on ideal flow. And in IFN transport, you can also get the directly. So if you calculate, sorry. Oh, what happened? Oh, there. Yeah, so you can calculate based on if you have the capacity, you can get all the values, the congestion, the and so on. Okay. So where this come from? That came from the stochastic matrix. Okay. So the earlier, so come back to index. So first you calculate the stochastic matrix. That means the probability to turn left and right. Okay. So once you have the stochastic matrix, yeah. So this is the stochastic matrix, right? Then you do in the earlier work, this is the matrix computation, the formula. Okay. But in the earlier work, what I'm doing is I'm doing random walk. Initially, I'm doing random walk. Yeah, with certain probability distribution in its intersection. Okay. So what happened is after some times, okay, the value of course going up and up and up, right? So the flow. Once you apply random walk, that means the flow will go up always. So that is not so useful.
You mean, sir, because there is a cost of getting from one node to another? Is that
No,
what you
I did
mean?
not even
Really
apply
getting
the
up?
cost. I did not even apply the cost at this point. Yeah, just doing random walk. And then when you run from one node to the next, you count as one flow.
Okay.
Okay. So, and then because the network is strongly connected, so the count of flow become increasing to infinity. So it's useless.
Okay.
So about 2 weeks, I'm telling, I think there is some pattern here, but I don't know what is that pattern. Yeah. So I try this different say between the centrality or whatever. Yeah. So centrality technique, but there is no real pattern there. Okay. But finally, what I'm doing is I just take the simple relative flow. Okay, so when you get the relative flow, suddenly, okay, the flow is going up to infinity, but the relative flow going to be integer. Always integer. And that integer represent that network. That is the initial discovery of IFN. Okay, that
Is that a unique integer?
unique.
Wow.
That's true. That's very interesting. Unique. Okay. Well, unique is a little bit strong word now. So unique in the scale.
Okay.
Okay. Unique within the scale. Okay. That means you can multiply by any number, then not unique anymore. Yeah. So, but the minimum will be unique. Okay. So in that case, that IFN, so at that time I still don't name it IFN. So okay, that distribution represent that network. Correct. And that is super interesting because now you can represent the entire network. At that time I was in Ateneo, so the entire network of Metro Manila into just one matrix, one vector. Right. That is wow. Okay. And then not only that, now you can change now. What happened if I change this network? Okay. Say I change the link. This one now close. For example, in your case, you want to close this one. Yeah. Or I want to open a new link. Or I want to increase the capacity. Okay. What will happen? I can simulate now without data. All the data I need is only capacity, which I can get from Google Map or OSM, OpenStreetMap. That GIS is already there. Okay. So, I mean, the data is already available. Of course, if you want to make it more accurate, okay, you need to have the real data, you need to have the camera, and then you get the actual stochastic matrix there in each intersection. But imagine how many links. I think there is 1 million links in Metro Manila alone. Yeah, more than 1 million links. If you in say more than 500, 600,000 intersection, small intersection, are you going to input camera in 500,000 camera in all intersection? Probably too costly. Yeah, at this point. So in that case, you need to get the approximation, correct?
Through probability.
Through probability. How do you get the probability? Probability you can get from anything,
The
right?
structure itself.
Yes. So in that case, one simplest approximation, not the true value, but approximation of probability is the capacity. Right. So, okay. I did not say this is the true value, but this is approximation. Better than nothing, because now you have, instead of installing camera, the whole okay, now you can just get the data of the lane width, for example, how many meter. That's represent probability also, right? Probability, you get the lane width compared to the whole lane width in the intersection, then you get the probability also. Okay, so approximation. Okay? Then you see, now I can approach that probability and then compute the entire network of Metro Manila without any data. In fact, you are architect, right? So you want to open a new city, which of course you cannot collect data, correct? So how are you going to collect? Based on your drawing, you compute using IFN, then you will know, oh, this one now become congestion. What will happen if I change this one? And that is very useful for new city. Correct. And then after that, hey, what happened if, yeah, at that time, United Nations CTPTO was calling me to give presentation in Vienna about nuclear and AI. Okay, so I said, oh, can we apply this IFN for AI. Okay, then I was enlightened. Yes, it's possible. So then you can see I can apply this IFN, exactly the same IFN I can apply for music, for text generation, for data science.
So isn't AI related to the Markov chain? So,
Well, yes,
so
not necessarily.
not
Yeah,
necessarily.
one of them. Yeah, one of them is Markov chain, right? So we, now we can apply this to many. So for example, robotic automation and power dynamic and prioritization. You can see there are many applications. Some even apply this to medicine. I don't even understand at all. Okay, so let them grow. So maybe you can apply this for your own study and so on. That's the purpose of giving this lecture, isn't it? So that you can use it in your daily life. And
So
that's
just
yes.
a few clarifications on the uh is this a type, are they types of IFN, the Premier, Cardinal, and Antigo?
Okay,
What
so
are
when you
they
have
just like
this IFN, so let's use it here. Yeah? I convert this capacity matrix. This is the capacity matrix. And then you calculate the actual IFN. Oh, what happened? So I have the capacity matrix here, and then I compute the IFN. So you see the actual IFN is kind of not integer, isn't it? So initially, this is what happened. Yeah, not always integer. Okay. Then I ask simple question, simple research question. Can we represent IFN as integer? That's the next question, right?
okay,
Okay.
so it's just like the same thing but represented in three or maybe
Yes.
more different ways.
Yes.
Okay. So, sir, last
Mm.
maybe because of your explanation, do you mean what a capacity matrix is just IFN but
No.
not
Capacity matrix is not IFN.
deliberated, but
No.
not deliberated,
Capacity matrix is not IFN because they are not premagic.
but I mean the the object, they are the same in maybe a potential or
Uh, Back to original idea, capacity matrix means the capacity, the number of lanes, the road width. Is this the same as the flow? No, right?
okay.
Okay. So
So
IFN is flow, meaning the
okay,
traffic flow.
it's the influence.
Yes. So this is just the influence of the resource allocation, the flow.
So IFN is like a measure that can be
Flow
derived,
is undefined. In this case, flow is undefined. Yeah. So you can define it because it's undefined, you can define it on your own.
but it is derived from the structure which is capacity
Correct.
matrix. Okay,
Correct.
okay. I think I
You
got
get it
it.
now. Yes. So, and definition of capacity matrix is also undefined. That means you define it, right?
Yes,
That
yes.
means you can apply it in other way. Yeah. I can apply this in economic of the balance distribution in import and export between countries, for example. So interesting.
Yes. Thank you, sir. This is very
Yeah.
useful.
So I hope you can see uh, the book there. If you have time, you can read. There are much more example of transportation and other related field, yeah, including agriculture there also.
Maybe just a thought. Uh,
Yeah, anytime if you have any questions or go ahead, no problem. Yeah.
maybe a philosophical. uh,
Philosophically, I mentioned a
I
while ago.
think
So this is ideal condition, steady state, long term.
I think the limitation would be you should know the current or the influence of each
But not
node.
necessarily. You can put 0 and 1. You should know the network structure, yes.
But deciding which is 1 or 0 is a
Oh,
decision in itself. So,
yeah, but you can see, you can observe this, right?
but the observation is still
Or
not decided by
if
although
you,
I think
that's why
I'm
we have
getting
strength of influence. Eh. So, for example, you observe there is, but maybe very small, then you just put 1. Okay. But you see that this is very strong influence, then you can put 9, for example. Right.
okay.
So because you are not sure that you can put different scale.
Like what do you call this? Temporary.
Temporary. And then you can start, you should start anyway with certain things, right?
Yeah,
So
okay.
then you can start with that, and then you see the value, and then you say, oh, this is not right. Okay, I will modify this one. Okay. But without the starting point, how are you going to analyze? So again, this is not one time you do and then you get, right? But I saw in your group project, you already have the network, yeah, and it is strongly connected already. So you can just put there and then input and compute, okay, and check who is actually the most dominant. Yeah? You also want to know, right?
Yes.
Right? So once you get the most dominant, then you start to ask, why this is the most dominant? Yeah? What this ring is about? Is this the one that create the dominant or no? No. How if I change this one? What will happen? And is this the target that you want? No. Then something wrong with my structure. Then you need to change. Right? How to make it so that then you record all the decision that you make, you record. Okay. Because without recording, you will lose. Right? So once you record from the beginning until the end, then you will start to see, oh, this is how my way of thinking. So you understand yourself better.
Yeah.
Yes.
That's a lot.
So I hope this is useful. I don't know.
I will digest this in
Yeah,
the next
slowly,
few
slowly.
weeks. Thank you, sir.
Yes. I remember last year, so the group, yeah, after because this power dynamic I put in the beginning last year, not the end. So yeah, and then at that time they suddenly create certain things that I even surprised. Yeah, okay. Some even apply military.
Wow.
The other one is dolphin or something.
Dolphins.
Yeah, you can check the YouTube. It is. I also shocked that they can very creatively use this. Yeah. So in Indonesia, I give this in business, and they start to analyze their own family business and so on.
Oh, wow.
And then they reported that, wow, this is very accurate. This is very correct. This is what happened. Even in my family, this is what happened. Oh, okay, that's very good to hear. Okay, so
Sir,
yeah,
maybe I'll just email
yes,
uh,
sure. Okay,
if I
anytime.
need.
Okay. Not only within the semester, you can, I mean, anytime. Okay,
Thank you,
after the
sir.
semester also. Thank you. In June, I'll be coming there
Oh,
in SURP,
okay.
so be proud
Wow.
also me. Yes. Yes, submission. What happened?
Hello, sir. This is just a short question. If I would like to ask if how's the mechanics again for the deduction of late assignments? How many deductions?
Supposed to be 1% per day, right?
Oh
But
my God.
I give merciful that I don't give that much deduction, right? So
Because I've actually around 4 assignments, I guess, for the last month since I got hospitalized.
okay. So you
If
tell
I
me
would be
that you are
able to submit,
hospitalized, that I can
but
remove
I can submit a
deduction.
medical certificate for that, sir, if necessary.
I think you already gave, or no, I forgot. Sorry, I
That
just forgot. Maybe am the one who forgot.
no, I will submit it
Huh?
tomorrow, sir. Tomorrow,
Okay.
sir. Tomorrow.
Then
I'll
I
just write it.
can recreate that. No problem.
Thank you so much, sir.
Sorry. Mm. Okay. Anyway, the minimum is I could put just 80. So if you, as long as you submit it, okay, will not go below 80. So in that case, everyone will pass as long as you submit it.
Thank you so much, sir. Thank you so much.
Okay. So I hope this is useful. Please spread the word about this and
Yes, sir. Very
use it.
useful.
Use in your. It's very interesting that, hey, I can just create the structure of what I'm observing in my
Yes.
surrounding. Okay. And
In
then
office politics or even in politics, home
yes,
politics.
yes, in home politics. And then suddenly, hey, suddenly I get new understanding that before I don't know, now I know. Right?
But for that case, sir,
Hmm.
another question
Yes.
regarding the discussion earlier, particularly in the arrangement of UN, the unfair,
Yeah.
for, yeah, for me, the unfair veto power, because for me, it doesn't make sense. Like everything that they do is only for show, just to show the world that they are convening. But if one of the Permanent Security Council said that I will veto this, everything will be nonsense.
Yeah.
So is there any mathematical loophole that we can utilize to bypass the power of a certain council? Like for
No.
example, Russia, he keeps on blocking the resolutions against him,
Uh,
or the system itself is broken and we cannot do anything about it.
uh, if you want to look at the history, before
Ah,
UN, there is a League of Nations.
low end. Mhm.
Okay, which is even worse than this one, right?
Really.
So, and if you look at the history from 1945 until now, yes, US is dominant in the world and probably not doing well, okay,
Mhm.
attacking other nations and so on. But if you are comparing the history back in several thousand years compared to 1945 until now, this is actually the most peaceful in human history.
Oh, I agree.
Okay. So yes, this is not perfect. Okay,
But
but
this is the best that we could get
this is the best what we could get at this point.
at
So
Probably
this
far.
at this point. That doesn't mean that you cannot improve. You can still improve. Okay, but
point.
to improve, you need to lobby. You need to create
Mhm.
influence. Okay,
Yes.
so
I love this conversation.
yeah, it is possible. Okay, one point that I want to tell you is don't undermine yourself that you think that you cannot. But there is possibility, okay, you're very young, there is possibility that one day you will be the most powerful.
Mhm.
It is possibility. Right? So just go to the right direction. That's the most important part, right? If you don't know the idea, so you don't know the direction. But if you know the idea, then you know the direction, then you go there. So eventually you will reach certain value, okay, that you want. Okay, as long as you keep doing in the right direction. But if you don't have direction, then what you will do is going here, going there. So you try all, but at the end of the day,
Mhm.
at the end of your life, you achieve nothing.
Mhm.
That's
That
not
I think that
the way.
that's a great takeaway, sir.
Yes.
For me,
Yeah.
the main point of IFN is not to actually solve things, but
Mm.
just to serve as a guiding compass of what
Right.
could have been the most perfect method for
Right.
arrangement
So the most ideal is
or
integrated
baseline.
and balance,
Mhm.
fairness. The meaning of IFN, the actual meaning of IFN is IBE, so integrated balance equilibrium.
Oh,
Maybe,
Oh,
sir, the reason why I mentioned there is limitation because we might see things that this is fair, but actually there is a greater. We are not omniscient to determine what is fair in
yes.
the greatest scheme of things because our knowledge is practically limited.
Mm. So,
And yeah, so
sorry. So, and
um sorry. What?
what did you say? Sorry.
Ah, so yeah, I think we might say things must be balanced, but what if
Oh, the
some things
situation is
should be
not balanced.
excluded or some things
Uh,
should really be excluded and that is fair in the I actually took a note here.
yeah, okay.
Maybe it's already corrected by having those excluded having zero influence as a part of the corrective uh,
Okay.
nature of the all networks. So
So,
I think that's how we can reconcile that.
so we have AI right now. Okay. So question is using this AI. So when I input it, the IFN power dynamic, it get guided misunderstand. Yeah. They think IFN uh, is the same as between us centrality or Markov centrality. So then we need to correct first until the AI understand this. Then they they start to give the correct answer. Okay. So that's number one. Number two, you are telling about yes, I have the ideal that I want to create certain balance and certain justice system and so on, and but this is not happening. Okay, no problem. Okay, but as long as you know which one it is, and you know that we can change the system, okay, and which change that you want, you have prioritization and so on. You want to know what change that you want in order to get what you want. That's design mechanism. Correct. So if you feel that you are powerless and you cannot do anything, then you are. Right. But if you think that, no, I can change the system, I can influence, and this is what to do, okay, then you are. You are what you have in your mind. Okay?
It's like having a language that some people might not recognize or have recognized but only realize intuitively. And having the knowledge of this would indeed help get
Yes.
some
Then
stream of
then
power.
then then influence the others. So the one that I'm teaching is actually influence the students, and then the students will go and tell the world, hey, there is a justice system that actually balance. Okay, and then you talk to others, and then the others will start to be influenced by you. Then it go beyond just one person or two-person. Isn't that what discipleship is about?
Mhm.
Right?
Yes.
So even the early church is doing the same. Yes, Paul.
so can I have a question? This
Sure,
is,
sure.
I just want to seek some advice
Yes,
related to our discussion earlier.
yes, yes.
Actually, this has been my dilemma for about 6 months now. Andrew knows this because he's
Okay.
my friend
Uh,
also last.
Sorry, this one is still in recording. So should I stop the recording?
Oh, okay, okay. Sorry.